processes. It's a confluence processes of fundamental mode into some higher order radial modes, and both of them are prohibited in a perfect state. But if you apply, for instance, a perpendicular magnetic field and tilt a little bit magnetization out of plane, and we see that the efficiency of three-magnon interaction increases. The same takes place if we apply in plane a magnetic field and shift our vortex from the central position towards the periphery. And the same, we see that processes becomes allowed and efficiency is quite high. So the conclusion is that symmetry breaking can open new three-magnon scattering channel. Another example is also very important for practice is a simple thin elliptic magnetic delta in a saturated state. It is very often used in various spintronic structures as some free layer or peanut layer. And if the dot is magnetized in the direction of the axis, spin-wave modes of this mode of the dot have clear symmetric or antisymmetric characters, as you can see here on these examples. From theoretical point of view, we found that in this case, symmetry of dipolar interaction reveals that only splitting into fully only confluence into fully antisymmetric modes is possible. So nevertheless, what is the primary mode? It could fuse only in modes like this one, like mode 5 shown here. And in direct simulations of nonlinear magnetization dynamics confirm this. Only at the point of resonance condition for these confluence processes, 1 plus 1 to 5, we see a decay of the primary mode and appearance of the second harmonic, which were imaged, and it's indeed the mode 5. But what happens if we perturb the state? And for instance, we can tilt the field in the plane, and we see that efficiency of other processes which were prohibited in the perfect state increase rapidly. And we indeed see the evidence of these processes on the nonlinear ferromagnetic resonance curve. We can apply a different perturbation, for instance, make a gradient field, and the result is the same. For some processes, efficiency increased drastically. Performing all the characterization for different possible perturbation, we found this table and showing that different symmetry breaking could affect selectively different channels, which depends on the symmetry of interacting mode. So when we need to affect some specific channel, we can look what type of perturbation we need to apply it and find a way to do this, thus to control a particular multi-magnon interaction process. And in fact, our colleagues was able to observe this in experiment. Here is experimental samples. It's the same elliptic three-layer dot, but here is underlayer so-called synthetic antiferromagnet, which is just two magnetic layers coupled with antiferromagnetic Erka-Kawai interaction. And this sub-underlayer could exist in different states. If it is in parallel state, so antiparallel magnetization, no peculiarities appear in the line with dependence on the frequency. But in a spin-flap state, when the magnetizations are non-collinear, we see strong non-linear damping, these two peaks. And the physics is indeed that which I explained before. In a antiparallel state, synthetic antiferromagnets produce very, very small and quite symmetric stray field. But in a spin-flap state, this stray field increase much more than one order, and they are quite non-uniform, having a very complex symmetry. So these fields affect our free layer and change the symmetry of the static state and open new channels for the three-magnon split. And with this, I would like to conclude. So I hope I was able to show that breaking of symmetry of static magnetization in a magnetic nanodelts is a powerful tool to mode selective and efficient control of multi-magnon interaction, and thus could be used for some engineering of nonlinear response of magnetic nanostructure and spintronic nanostructure. And user detail will be published in this work, which should appear next month. Thank you, and welcome to answer your questions.
Okay, thank you for the nice report. And now time for the questions, please. One question or two, we have time.
Okay. As far as I see, your research is mostly fundamental, but I have also seen very sophisticated nanostructure. Which devices will be built on the base of such nanostructures? What's their applications?
Okay. The presentation is always switch off. Okay. The device which I show, it's a typical spintronic valve. Indeed, the application-related devices, which could be considered as a memory cell. So this free layer changes its magnetization. It's like a magnetic memory. Another application is microwave generators or microwave diodes. Also this spintronic structure, and especially for this microwave application, nonlinear damping is very important because this device all works in nonlinear regime, and we need to know and to control this nonlinear damping. Exactly this 3-magnon confluence is one of the main nonlinear damping channel.
Okay, thank you very much. And now we come to the next reporter, Professor Galina Rudko from the Lashkaryov Institute of Semiconductors Physics, National Academy of Science of Ukraine. Please, Galina, floor is yours.
One moment, we have one more question, and then we will.
Okay. Just limited in time. Okay.
This process of spin when you have the spin flop.
It depends on the mechanism. If it is a precessional switching, it's about tenths of nanoseconds. If it is fast mechanism, so one half of period flip, it's hundreds of picoseconds.
Sure. Thanks. Okay, thank you. Now we can move to the next speaker.
Hello, everybody. And I would like to start with the words of deepest gratitude to our organizers for possibility to present and report our results at this conference. And the title of my report is Light Emitting and Non-Radiative Processes in Cadmium Sulfide Nanoparticles Started but Optically Detected Magnetic Resonance. And I will present the results obtained by this group of researchers, who are all of them are from the Institute of Semiconductors Physics, Kyiv. Oops, once more. Okay. I will speak about light emitting species, light emitting particles, which are very important for future applications. We have nanoparticles which are characterized by a wide variety of specific spectral features. And up to now, we know that spectral features can be both very narrow and up to very wide, even white light emitting particles. Therefore, each species has its own explanation of the origin of luminescence. They range from band-to-band transitions or excitonic radiation, or maybe donor-acceptor pairs radiation, also self-trapped excitons, some spectral features from surface, some states. But there is no consensus about the origin of luminescence, even dealing with the only one type of features. And moreover, even less information we have on the non-radiative transitions and about the ways how the energy of photoexcited electron-hole pairs is dissipated. What are the passes to the dissipation of energy, which particles or which species take part in this energy relaxation. So this report is devoted to analyzing those non-radiative paths and those energy relaxation processes in nanoparticles. And we apply the optically detected magnetic resonance methods, which is a combination of traditional EPR method, electronic paramagnetic resonance, with photoluminescence. When we detect the magnetic resonance by the changes of the intensity of luminescence. Our choice of the objects is a nanocomposite. Nanocomposites are, their properties are due to the properties of their components. Nanoparticles have many advantages listed here, which you mostly know. And the matrices, in our case, we use the matrix from polymer. Both components are very attractive, but it should be stressed that nanocomposite properties of nanocomposite are not a simple sum of the properties of its components. There is interaction between our components. For example, it can be new state of surface of nanoparticles, or it can be energy transfer between nanoparticles in matrix, or charge transfer. So, our choice is the nanocomposite that produces white light, because it can be used in our everyday life for lighting. Here are the details of the synthesis of our samples. We used a simple colloidal wet chemistry route. The advantages of our method are using water solutions, also using room temperature, and we regulated the size of nanoparticles by composition of the solution and by the time of ripening. Here are presented the chemicals which are used for the synthesis, and I show the typical sizes of our nanoparticles. Later on the next slide, I will prove that these are real sizes not predicted of our particles. After the ripening of colloidal solution, we added gelatin to the solution and obtained composite nanoparticles in polymer. Then it was dropped on the glass plates, and we obtained thin film samples. The sizes of our nanoparticles were controlled by two ways. One way is the optical absorption, and on the left panel, you see the typical size-dependent shift of absorption edge, and even excitonic features. From this shift, we were able to calculate the sizes of nanoparticles. Very nice for us is that the electron microscopy supported our calculations, and on two other panels, you see the photos of our nanoparticles. And on the right side, you see the distribution of sizes. So optical and electron microscopy data coincide. This slide shows the luminescence and ODMR spectra of the samples with different sizes. Maybe it is not well seen in the last rows, but the lower spectra correspond to small nanoparticles and the upper to the larger. So from up to down, it's 6, 3, and 2 nanometers. It is seen that luminescence of our particles is very wide. It is seen by the naked eye like white luminescence. And the spectra are rather similar for the samples with different sizes of nanoparticles. On the contrary, ODMR spectra, which are shown on the right side of the plot, change drastically. For the larger particles, we see two narrow signals, one negative and one positive. And with the increasing of the nanoparticle size, the positive sign shifts to lower fields and splits. We observe the doublet. Let's discuss both types of signals separately. We will start with negative ODMR signal. The negative signal, it means that the center, this paramagnetic center, which is participating in magnetic resonance, is the center of non-radiative recombination. Magnetic resonance causes the diminishing of photoluminescence intensity. The G factor of this paramagnetic center is 2.004. So it can be concluded that this center is the isolated center with trapped electron. And both the position and shape of this negative signal do not depend on the size of nanoparticles. In our previous studies, we have ascribed such a signal to the sulfur vacancy, which is acting as a center of non-radiative recombination. And here is the reference to this paper. As to the positive center, with much more complicated behavior, the positive side of signal means that this center corresponds either to luminescent center or to the centers involved in the relaxation of photoinduced carriers before photoluminescence. As our photoluminescence spectra are mostly independent on size, and these spectra very, very strongly with size, we can conclude that our center corresponds to the path of relaxation of photoexcited carriers. Moreover, G factor value is 1.95, which also points to the electronic feature. Also, the splitting is a very characteristic feature for this signal. The smaller the size, the larger splitting in the doublet. Okay, based on these facts, we can make the assumption. The presence of doublet signal in this composite is due to the exchange interaction of some centers, paramagnetic. One of them have trapped an electron, another have trapped the hole. So when the size of nanoparticle decreases, the distance between these centers also decreases. This causes the increase of exchange interaction due to the diminishing distance. Sorry. Having in mind this assumption, we had simulated our spectra using traditional spin Hamiltonian consisting of three terms. One term describing hole center, another electron, and the last term is responsible for the exchange interaction. We managed to simulate our spectra very nicely, and here we present the parameters used for simulation. The right oval shows us that simulations supported the idea about increasing exchange interaction with diminishing size. But up to now, we know nothing about where the paramagnetic centers are situated. To find out at least some information about this, we did a very slight or very tender treatment of our samples. How can we change the interface? In this case, we decided to make moisture treatment, just to drop some water on our films and then let them dry. The result obtained was rather impressive. While the photoluminescence almost did not change, maybe 10 to 15% in different samples, the ODMR signal of the positive sign completely disappeared. What does it mean? It means that one of the centers which is involved in exchange interaction is influenced by moisture, so this center must be situated on the interface. And based on our results, we present the following conclusions. The doublet positive signal of ODMR is related to the complexes of paramagnetic centers, which are formed by electron trapping and hole trapping centers, and they are involved in the exchange interaction. As the size of nanoparticle decreases, the distance between this couple of paramagnetic centers decreases, and exchange interaction increases. Correspondingly, splitting also increases. And by moisture treatment, we have shown at least one of these centers is located at the interface. As to sharp negative center, it is related to the non-radiative center, And most probably, as it is not influenced by moisturizing, it is situated in the bulk of nanocrystals. Thank you for your attention.
Thank you for your report. And we have one question, very short, because we are limited in time.
Yes, we have one question in the hall. One moment.
Can you conclude based on your result that smaller nanoparticles is more perfect without low quantity of defects compared with higher nanoparticles?
Most probably we cannot conclude this. We just see that the defects are more close, and this is the reason for what we see. We cannot conclude that. We only practical conclusion can be that if you want to increase the intensity, you can to avoid non-radiative recombination. Just you have to avoid sulfur vacancies, but it's a question to chemists how to do this. Thank you.
Okay, thank you very much. And now the time for the next reporter. Dr. Yulia Bondar from the Institute of Environmental Geochemistry of National Academy of Science of Ukraine, please. Floor is yours.
Today I will present the oral report, stabilization of cadmium and other heavy metals in contaminated soil, but composite zeolite granules coated with iron oxide nanoparticles. This work was carried out in the Czech University of Science Prague with colleagues from State Institute, the Institute of Environmental Geochemistry in Kyiv. It is well known that potentially toxic metals in soils pose long-term health risks to both ecosystems and humans. Cadmium, one of the most significant negative effects on all biological processes in plants, animals, and humans. The World Health Organization has classified cadmium and cadmium containing compounds as a first-class carcinogens. On this slide, you can see the main anthropogenic sources of soil pollutions. Anthropogenic sources are responsible for more than 90% of cadmium release in the environment. The most important anthropogenic sources in soil pollution include domestic and municipal waste, industrial activities, agricultural activities, and military activities. That is why it is very important for Ukraine, mining and petroleum-derived products. They cause soil and water pollution with toxic metals, including cadmium, pesticides, and organic contaminants. Soil is the most important thing for metals and act as a barrier to prevent their entry into the food chain. Hence, remediation of cadmium-contaminated soils has become a hot research topic. How to remove the tasks to remove contaminants from soil is not very easy task. That is why we use a stabilization solidification technique for in situ soil remediation. The soil remediation by mineral amendment with reactive minerals as carbonates, phosphates, clay zeolites, and metal oxides is a base for stabilization solidification techniques that reduce the bioavailability of toxic elements. The main advantages are cost-effective, environmentally friendly technique, easy to use, and this technique can be applied for large areas of contaminated soils without altering the natural soil functions. So we can consider this technique as a green technology. Among the mineral amendments used for stabilization heavy metals including cadmium. Natural zeolites have attracted attention because of their rather high absorption ion exchange capacity and low price. But there are some limitations for its application in soils. Low absorption capacity and selectivity for heavy metals, possible desorption is a sources of recontamination, and long-term behavior of zeolite in soil environment is purely understood. Also, we know that metal oxides as manganese oxides and iron oxides can be used to stabilize heavy metals in soil. Within the iron oxide family, ferrohydrite is one of the most highly reactive species because it's present as nanoparticles in soil. The main advantage is high surface area, huge absorption capacity, and strong interaction with heavy metals. But the limitation, ferrohydrite synthesized as nanoparticles, which are difficult for practical applications. And also we know very pure, our knowledge about the impact of nanoparticles over the soil is very pure. That is why we decided to combine these very attractive minerals to synthesize composite zeolite with iron oxide nanoparticles covered the surface of natural zeolites. Our approach for synthesis in situ formation of iron oxide nanoparticles on the surface of zeolite supporting matrix. As materials, we used Ukrainian zeolite. It is a clinoptilolite rich tuff from Sokernica deposit. It's characterized by a high content of clinoptilolite, and based on the silicium aluminum ratio, the clinoptilolite tuff was attributed to the zeolites intermediate between high silica hyalandite and low silica clinoptilolite. So it's characterized by high thermal and chemical stability. For experimental work, the grain fraction of between 1 to 2 millimeter size was used. Other materials we used is soil contaminated by heavy metals. The soil was put from Spain in near the valleys, and it characterized by a high concentration of heavy metals, including cadmium. On this, we used two step of experiments. On the first step, we prepare samples by white time deposition of iron oxide nanoparticles, and ferrum contents is about 2%. And the second step, we prepare composite samples by 2 times iron oxide deposition, and iron contains more than 4 weight percent. And these composite materials we used for our experiment. On this slide, you can see the same images of the composite granules in CE and BCE mode. One can see that the iron oxide phase homogeneously distributed on the surface of the light. And under the high magnification, one can see that the iron oxide layer consists of rounded submicronic particles, which appear to be agglomerates of nanosized ferrihydride particles. On this slide, one can see that very small iron oxide nanoparticles with homogeneously distributed on the surface of the light granules. We investigate the absorption of cadmium in 3 experiments. The first experiment, we used cadmium solution in sodium nitrate solution. Also, we carry out experiments from soil solution, absorption experiment from soil solution. The soil solution was prepared by shaking the selected soil in deionized water for 1 month, and also we carry out pot experiments. The zeolite and composite zeolite granules were incorporated in the pots containing soil for a period of 12 weeks, and after this period, the zeolites granules were examined by them. One can see on this slide, you can see the cadmium absorption from monocomponent solution. One can see the very not very absorption of the natural and composite zeolite granules is a 2-step process with a long second period. For the natural zeolite, equilibrium absorption was reached after 40 hours, whereas for the composite zeolite granules, it was reached after 100 hours. We found that kinetics follow the second order kinetic model. That means the rate limiting step is hemisorption. Also, we investigate the absorption isotomes and found that the absorption of cadmium follows the Langmuir model better. That the Langmuir model better describes the experimental results on cadmium absorption than the Fredlin one, which assumes monolayer absorption and uniform distribution of active sites on the adsorbent surface. The deposition of iron oxides layer on the surface of the light granules led to an increase in the absorption cadmium absorption capacity. On this slide, you can see the results of absorption from soil solution. One can see that soil solution contain heavy metals such as cadmium, lead, and zinc. And you can see that both natural and composite zeolite granules are good absorbing materials for heavy metals from the soil solution, and composite zeolite granules are more effective in absorbing cadmium ions. On this slide, you can see the results of pot experiment after exposure of 12 weeks. This experiment demonstrated high mechanical and chemical stability of the composite zeolite granules in the soil environment. And also we can find on the surface of composite zeolites presence of heavy metals such as zinc and lead. And heavy metals fix to the surface of composite zeolite granules and associated with the iron oxide phase. Unfortunately, we got puzzle puzzle results with natural zeolites because no heavy metals were detected on the surface of the natural zeolite granules. Low concentration of heavy metals as zinc, lead, and copper found locally, and this localization may be associated with weathered areas, natural oxidation. That is why we proceed our investigation to understand why we cannot find heavy metals on the surface of natural zeolite granules. And conclusions that we, using simple synthesis technology, we obtained composite materials which are very effective for stabilization of heavy metals in soil environment. Thank you for your attention.
Thank you for your report. Now we have time for short questions. Okay, please.
Thank you. Have you tested the stability of your zeolite composite after absorption of cadmium in different temperatures, say, which could exist in our region, say, from -20 to +50, something like this?
For what reason?
To see if the absorption still is not if the absorption can occur, say, at elevated temperatures.
Our aim was investigate the behavior of zeolite and composite zeolite in soil environment. Soil environment, it's low temperature environment. That is why not need to increase temperature and investigate the stability. If it will be interesting, we may carry out this experiment, but it's not without our aims.
Thank you.
Okay, thank you for a nice report, and we come to the next reporter. So, Professor Igor Virt from the Ivan Franko Drohobych State Pedagogical University of Ukraine. Please, floor is yours.
Good morning. My presentation, low frequency noise zinc oxide film deposition of the PLD method. Show slide introduction, experiment technology and methodology, electrical and optical characteristic of structure zinc oxide, noise characteristic of structure zinc oxide, leak sensitivity device base transition zinc oxide. Introduction. The article presents the result of study noise characteristic in film zinc oxide. Film groove laser deposition.
We need to correct the image in the conference hall because we have a problem with translation. One moment.
Chief presentation of characteristic zinc oxide of practical application zinc oxide materials, of properties zinc oxide, and material base zinc oxide. Research data have raised practical motivation, precisely monitoring of ultraviolet radiation and communication system, but for motivation, paper James et al. Empirical and production ultraviolet aircraft signature and paper Giza ultraviolet simulation approach warning system testing. For slide presentation technology and methodology deposition chin films. Setup of base laser neodym jak, primaire and second harmonic. This image presentation chin films for substrate silicon and setup deposition chin films. Key presentation for properties technology deposition chin films, intensity beam laser, pulse length, intensity and duration for impulse. Key slide presentation X-ray diffraction, unstructured properties chin films, chin film zinc oxide doping NIC 110%, and the image chin film oxide substrate silicon and image structure microscope of size grain zinc oxide. For presentation 200 orientate for size crystallite zinc oxide and calculation constant particle size zinc oxide. As electrical optical characteristics zinc oxide, cheap presentation dependence resistance of temperature, observe doping NIC donor level different level and optical properties. One hub thin films oxide 3 electron volt for practical application device ultraviolet and noise characteristic. Noise characteristic measurement band switch 210 kilohertz, setup presentation this slide, application amplifier Unipan and setup oscilloscope for production fast Fourier program fast Fourier transformation and measuring current fluctuation box and chin films. The presentation time domain for measurement and program transformation frequency domain for open Windows Blackman, presentation for slide. Calibration of resistor thermal noise measurement and presentation of his power spectral density for Y and X frequency. Presentation setup measurement chin films, amplifier, FFT transformation, and Windows domain frequency. Presentation equation noise mechanism noise summer thermal and low frequency and generation recombination. Plot low frequency noise zinc oxide, temperature dependence, and present production Y frequency and power spectral density of frequency. The equation generation recombination noise and carrier concentration carrier tau. Noise characteristic model temperature Duta Horna for density function D, distribution of temperature, and production structure photosensitivity structure zinc oxide for silicon. The observer setup, basic setup for measurement signal, photovoltaic signal of oscilloscope for illumination UV light. Presentations schema interface energy silicon and zinc oxide and mechanism photoconductivity photosensitivity of structure zinc oxide silicon, and observe parameter characteristic sensitivity structure zinc oxide and silicon photocurrent and detection and quantum efficient external EQE. And calculation noise equivalent power structure thin films zinc oxide and silicon NEP for calculation photosensitivity and level noise. And conclusion. The epitaxial law zinc oxide semiconductor produce laser deposition, its spectral electrical properties study, noise spectra, power spectral density for measurement and dark and ultraviolet light, and from sensitivity heterostructure based zinc oxide silicon interface for calculation. literature, and thank you very much.
Thank you very much, Professor Wirth, for your nice presentation. So we have time for questions, please. Are there any questions?
No question in the hall.
Okay, then maybe we invite the next our reporter, Professor Igor Shtablavy from the Ivan Franko National University of Lviv, Ukraine. Please, floor is yours.
Good morning, everyone. My name is Igor Shtablavy, and I am working in a scientific group of Professor Mudry from Metal Physics Department at Ivan Franko National University of Lviv. Work, okay. During a long time, we investigate disordered systems, liquids, amorphous metallic alloys. And now I want to present you our result about formation of the ferrum-based bulk.
Something happened with the online microphone. I don't know. I cannot hear you.
Okay. First of all,
Now, okay. Mm-hmm.
Okay, is this good? Amorphous alloys, metallic amorphous alloys attract to themselves great attention due to unique physical properties, physical and chemical properties. Such materials have a good mechanical properties, corrosion resistance, magnetic properties, and others. These unique properties are mainly affected by presence only short range order, like in liquids, and absence of long range order, crystalline structure, grain boundaries, and so on. For obtaining such alloys, doesn't work. Okay, thank you. To obtain amorphous alloys, metallic amorphous alloys, in classical way, we can use rapid solidification from the liquid state and form in such a way thin ribbons or tapes of metallic amorphous metal with a thickness of few tens of micrometers and up to few centimeters in wide. Also, these materials can be formed in forms of powders, amorphous powders, also by solidification, rapid solidification of liquid. And in such a way, we can obtain powders, amorphous powders. Only some metals which are characterized by differences in atomic radius and crystalline structure, only these metals or alloys can form bulk, so-called bulk metallic glasses, but the sizes and cross sections of these bulk metallic glasses are no more than a few centimeters in size. But we need a possibility to form amorphous metals and alloys in large sizes and uniforms and different forms and sizes. For this, nowadays, it is important and helpful method of additive manufacturing. And for obtaining metallic materials, most used the method of selective laser sintering and selective laser melting. For formation of metallic glasses, bulk metallic glasses, in modern technologies, selective laser melting mainly is used. This method use laser beam like is presented in this figure. Okay, here, laser beam forms liquid pool, and due to the fast moving of laser beam, this liquid pool can move and melt and cool with large rate and large velocity. And in such case, we can obtain a rate of cooling, which is near to rate of cooling for formation of amorphous alloys. And for this, using this method, we can use, we can obtain bulk metallic glass, and this picture was obtained from internet to present you possibilities of such method. For iron-based amorphous alloys, we can say that these alloys have unique magnetic properties. First of all, they are cheap materials because iron is a cheap material, which is the main component of these alloys. The main factors that affecting the properties of obtained alloys by selective laser melting are the power of laser irradiation and scanning speed. And in our investigation, these two parameters was changed only. But in formation of bulk amorphous alloys, the main problem is the formation of cracks, porosities, and others. To avoid cracks, we can make several changes. In one way, we can use higher laser energy or low laser energy to change porosity of materials. In other way, we can control porosity and cracks, which are presented in this photo. We can change these cracks by addition of other metals with low melting point, such as copper or copper and nickel. In our work, we have investigated such alloy. Liquid amorphous alloy was chosen to study the effect of low power laser irradiation on phase transformation and formation of bulk amorphous composites. For obtaining such alloys, we have used low energy selective laser melting. Amorphous ribbons were 25 micrometers thick and 2 centimeters wide. Ribbons in this work, we have used ribbons and powders, which was obtained and formed from these ribbons. They was irradiated with laser power of 15, 25, and 40 watts with scanning speed from 1,000 to 4,000 millimeters per second. For phase analysis, we have used X-ray diffractions methods, and electron microscopy analysis was used to investigate microstructure of obtained amorphous alloys. In this part of my presentation, I want to show you results on laser treatment of ribbons at different power and different speed of laser processing. In these conditions, velocity 4,000 millimeters per second and power 50 watts, only round spots on amorphous ribbon are shown, and this spot was formed due to laser ablation of surface of amorphous ribbon. At another laser treatment modes, we have obtained similar results, and here we show that at higher at low velocity, we have obtained strips of laser of material of strips formed by laser ablation of our amorphous metals. In this case, X-ray diffraction analysis shows us that structure is fully amorphous. At higher power, laser power, we have obtained the melting of lasers of spots in materials, and at the edge of these spots, we have obtained flashes that confirm the melting of materials. At lower velocity, these splashes are merged and forms lined slides. At higher, at lower velocity, we have obtained the melting of amorphous strips and damages of them. In this case, at the lower velocity, the crystalline phases are formed. At the higher laser power, the melting of amorphous alloys is observed at all velocities. And in these pictures, you can see the results of such treatment. But the main part of our work is the analysis of formation of bulk amorphous alloys from amorphous powders obtained on the base of previous amorphous strips. In this slide, you can see electron microscopy analysis of bulk alloys without copper. These powders were treated with laser beam with power of 25 watts and the velocity 1,000 millimeters per second. And here we can see a significant degree of porosity and the presence of higher amount of iron-based nanocrystals, which are clearly seen on this picture. When we add copper to this powder with amount of 50 weight percent and laser beam has also power of 25 watts at velocity of 1,000 millimeters per second, we have no observe any good transformation in microstructure. There are also large porosity in materials and formation of nanocrystals in the bulk alloy. This alloy is mostly crystalline and polycrystalline. Here we see the grain structure, and this alloy was prepared using laser power of 40 watts. And composite, we can see that composite contains a significant amount of crystalline phase, and copper in these alloys is aggregated in the form of large inclusions at grain boundaries. Better results was obtained by us when the hedge spacing, so-called hedge spacing, which means that distance between two laser tracks was lower and was 30 micrometers. In this case, more uniform structure is formed, and the dendritic structure of matrix is formed, and copper nanocrystals are assembled in the interdendritic regions. Our results of X-ray analysis confirm the presence of a lot of crystalline phases, but some traces of amorphous phase is presented here. Presenting of amorphous phase is confirmed by DSC investigations. And here, by the red line, we can see DSC line for amorphous ribbon. And by black line, we can see the bulk results from bulk amorphous alloys with copper inclusions. And in both curves, we have obtained peak which shows us the crystallization of amorphous phase. And now I want to present conclusions. And the main conclusions, I can say that addition of copper to the amorphous powder leads to the formation of small-scale composite with a copper inclusion and a significant transformation of the matrix materials. In our case, some part of alloy was amorphous, but there was crystalline phases which form after laser radiation. Thank you for attention. Maybe you have a question.
Okay, thank you for report. Yes, one short question.
How did you confirm the existence of amorphous phase? Maybe you have a nanocrystal alloy with amorphous boundary, but on XRT spectra, you have the peaks with crystalline phase.
Yes, we have X-ray diffraction patterns which shows that we have a main part of materials in crystalline state, but differential scanning analysis show us the crystallization peak, exothermic peak, which obtained after crystallization of rest of amorphous phase in our alloy.
Peaks. Initial material was without peaks.
No, that was maybe I cannot to show you last. Okay, here we have on the red this line. This peak is confirmed as the crystallization of amorphous alloys of such concentration, and here we have a smaller peak which confirm as the crystallization of the rest of amorphous phase in alloy.
But as for me, you have nanocrystal materials with amorphous boundaries.
Maybe. Thank you.
Okay, thank you very much.
Thank you.
Okay, thank you for your report. And now the time for the next our participant. It's Dr. Lyudmila Barkovska from researcher Yuri Seroshkin, Lashkaryov Institute of Semiconductor Physics of the National Academy of Science of Ukraine. Please, floor is yours.
Sorry, Lyudmila Borkovska contacted us and told that she will not able to make a presentation now, so we should move to the next.
Okay. So the next reporter will be Dr. Miroslav Sushko, electrical percolation in composites with a segregated filler distribution from report from Odessa, Mechnikov National University of Ukraine. So Dr. Sushko, are you ready?
Hello. So should I present my report right now? Yes.
Yes, because one reporter is absent, so
Okay.
be a little bit shifted.
Okay, yeah, I am ready.
Okay, you're welcome.
Okay, let
Floor
me
is
load
yours.
up my presentation so I can manage it, right? Hold on, something wrong. Can you see? Can you see my presentation?
It's open.
It's open, okay. Hold on a second.
I see that Miroslav has started screen sharing, but I don't see the picture in the Zoom. I mean presentation is absent somehow. Oh,
Okay.
now I see. Yes.
Yeah, you see, right?
Okay.
Okay. So the title of my presentation is Electrical Percolation in Composites with a Segregated Filler Distribution. And here briefly, I outlined the points I would like to discuss. First of all, I briefly discuss what is shell order or segregated distribution of filler particles. So this is special types of composites. Then I discuss a model, hardcore penetrable shell model for electrical conductivity, which actually has been developed earlier by us for random distribution, but actually it was developed in terms that can be revised for shell order distribution of particles, and then I demonstrate application of the model to system, real system. So what is segregated type, hold on, segregated filler distribution? Over here you see on the right typical random distribution of filler particles. So usually our composites are usually particles dispersed in some medium, non-conducting. Usually this is a polymer. On the right you see so-called segregated or shell ordered. Segregated, it's much wider word. Shell order, this is particular type of segregated filler distribution. So over here you see, and these polymers were developed by Mamunia and Alice. At Alice, over here you have citation. So if you take a look at these polymers, so you see over here you have polymer globes, and you have black dots. This is filler, metallic filler. In this particular case, this is nickel particles. So preparation is pretty simple. So first you have a mixture. You prepare a mixture of polymer large globules. So this is white, and carbonyl nickel powder. Then place them in a hot die at 170 degrees and pressing them after 1 minute. So actually, you obtain this distribution. Optical pictures of these polymers I will show later. Over here, you have electrical conductivity measurements, the results. So you see over here, you have polymer and filler particles. So PVC is polyvinyl chloride cuprum, and this is epoxy resistance cuprum. And over here you have the same polymers, but nickel particles. So 1 through and 4, this is polymers composites with typical random distribution. And for this particular case, we have another curve. This curve is number 3. So you can see, so if we talk about random particle distribution polymers, so they demonstrate similar behavior. Yes, but over here you see you have some shift, for instance, for percolation threshold. And the slope of this curve is actually different in contrast to this situation. So our problem was to try to develop a model which could explain or at least suggest some approach to description of these kinds of polymer. So what do we use? We actually use so-called hardcore penetrable shell model. Over here you see it. So this is model in general terms. So these black dots represent cores. This is actually a so-called nucleating center for formation of the microstructure. They are surrounded by some shell. We assume the shell is penetrable. And over here you have a matrix where all these components are embedded in. And over here you have the description. What is very important, we assume hardcore penetrable shell morphology. What does it mean? So when these two particles, the core and the shell, approach each other, these shells can overlap. So this is actually a mathematical model, but after you prepare a composite by embedding such particles into some media, you will get some microstructure, and you can see that the components, the amount of the shell, so the filler concentration, the shell concentration, the matrix concentration can vary. So this is very important. This is not fixed. And to develop this overlapping, we introduce two simple rules. So we assume that if you, for instance, over here, L is the distance to the point of incidence to the center of the closest particle. So for instance, if you have this particle, and you are located at the center of the hard core. So if the distance from the center is smaller than the radius, we assume that the complex permittivity of this core is epsilon c. If the distance is greater but less than the outer radius R2, this is shell. And if greater than the outer radius of the shell, this is the matrix. But what is very important, key point in this model, you have overlapping on the shells, and that means we have to define what happens when you have point as overlapping in some regions. And for this case, we, besides this rule, introduce so-called rule of dominance for overlapping regions. What does it mean? It means that, for instance, when you have overlapping of hard cores with the shells or the matrix, the electrical properties of the core dominate. If you have shell overlapping with the matrix, they also dominate all the matrix. So this is the rule. You have to combine these two suggestions, and this can be done using so-called descriptor or characteristic functions, as I show right now. So how do we treat So the idea is what? The idea is what? You have to consider to analyze this model, you have to determine the electric conductivity of the system using these suggestions and obtain some quantitative relations, and then you apply this model to different types. So if you have, for instance, random distribution particles, random distribution of the particles, so this is these dark circles are just the particles themselves. In the case of segregated distribution, we should treat this dark cores as polymer globes, yes? And the shells again may have different nature. If you have random distribution particles, you can assume this is the region which takes into account different interface phenomena, which of course occur near the surface of the particle. If you talk about segregated field distribution, of course, you have to assume this shell consists of the particles, of the filler metallic particles, plus, of course, you have some patches of the polymer. So this is actually the mixture. And it's clear that when you introduce the new particles to the system, increase the concentration, of course, these shells will be changing, overlapping, and so on. So we need to harmonize this system. We have to calculate the effective permittivity, and this can be done. So I just briefly tell the ideas. I won't go in the details, but the idea is very simple. First, so qualitative ideas. What does it mean? We consider the case when the probing field radiations is very long. So actually we approach to the quasi-static case. So you see lambda becomes very greater. So when we consider the system tested by this long wave radiation, actually the system can be with good accuracy considered as a composition collection of some group of particles. These groups include very large number of particles. They are microscopic, so their physical properties actually reproduce the properties of the entire system. But on the other hand, the size of these particles, even though they are microscopic, is negligible compared to the testing radiation. And this is very important thing, because this fact means that the main contribution to the field forming the properties of this macroscopic region are due to the regions where the distances are very small compared to wavelengths. And that means what? When we try to describe the field inside this system, we can take advantage of this fact. Look here. So look, we consider that our system consists of, is equivalent to some fictitious media into which the particles and the matrix are embedded. So we can write down the local complex permittivity as this effective matrix plus deviation caused by such macroscopic group. Such macroscopic group we call the Kampa group. So this Kampa group introduce some deviation from the matrix, efficient matrix, and we can model this deviations using some apparatus of indicator functions. But for now, it's enough to just know that when we write the equation of propagation of the electromagnetic wave in this field with some distribution delta epsilon and epsilon f, we have this differential equation. We can, using standard procedure, change to the integral equation where t is the green function or the propagator of this electromagnetic propagator for this equation. And then again, following standard procedure, we can use iteration procedure to represent the ends in the form of the iterative series. So we solve this equation like that, and we have field not affected by the inclusions, plus the field due to many particles, re-emissions and correlations effect in this system. So this is standard form. If you take a look at this, it consists of products of these propagators, which electromagnetic propagators, and deviations at different points. So this is standard approach in multiple particle scattering. But what is important? What is important? How do we deal? We have in this equation some propagator, this green function. It has this structure, but if you consider a macroscopically homogeneous and isotropic media, we can take advantage of special representation for this propagator. So what does it mean? We can replace this accurate, exact propagator, but some expression, t-title, in the meaning that for good enough function, any integral from the actual propagator and any integral with this this representation gives the same results. This is very important. So it's well known from some mathematical physics. In some cases, you can take integrals using some so-called delta functions or whatever without knowing many details about the function itself. So we use special representation for the propagator. This special representation for propagator is well known in the literature, and these three special terms are given over here. So the first term, this is, you see, it has delta function, and this part of this T represents short range re-emission. So they correspond to a re-emission between closely situated particles inside the compact group, which themselves are macroscopic, and on the other hand, the distance between them is small compared to the probing test radiation. Over here you have another term. It describes long-term radiations between these compact groups, between any inhomogeneities, and you have another term. So you have these three terms, but look here, if you take into account this formula, this angular part, you see after averaging or macroscopically isotropic medium, this term becomes simply zero. So after averaging, this term vanishes, and this term, when you approach to long way limit, k approaches to zero, is much smaller than this term is much smaller than this one. So this third short range re-emission contribution to the propagator survives only after averaging. And that means what? Whenever you have this solution, in this solution, after averaging, you can replace the actual propagator by its short re-emission part, which is a delta function. And since this is a delta function, you can take these integrals to any order. So the result, I just explained the ideas because this is not very thin, but the idea is over here. If you want to find the effective permittivity, you can find as a proportionality coefficient between the complex current and the complex field. Using this formula, you can find this explicit expression for current and for electric field in terms of the compact group contributions. And these compact group contributions you model according to the structure of your system. Over here you have this this model for our particular case. Over here you have delta epsilon m. This is deviation or matrix from fictitious media. This is characteristic function of the shells. So this, when you get into this area, if you miss the core and if you miss the shell, you get into the medium, and the contribution at that particular point will be due to the matrix. If you get into the core, the contribution will be due to the core, and so on. So operating with these functions is very simple, and therefore calculations can be carried out. And what is very important in this approach, we can use internal closure condition, and this condition follows from some general requirement. For instance, you can require that for conductive systems, standard conditions, boundary conditions for media should be valid also for homogenized media, so the media with effective properties. And this allows to close the system, to close the model. So this fictitious media into which you embed all components of the systems is just the effective media, so it's like a Brueggemann approach. So at now, you can calculate the moments. The moments can be calculated and expressed in deviation from the effective media. And what is very important in this expression, you have the concentration of hard cores, and also you have the concentration of these penetrable, hardcore penetrable shell particles. For this expression, we have some results from statistical physics, so these results are very good, very well justified. So actually, this procedure allows us to find the equation for the quasi-static effective conductivity, and this equation is over here. So you see, phi is the volume concentration of the particle and the shells. This is the medium. Sigma conductivity of the media, this is the concentration of the cores, and this is the concentration of the shells. So for each quantity, we have some expression. In case if you have inhomogeneous media, you can generalize this equation. So this is, at this point, we have used no suggestion about the physical nature of our particles. What do we have now? Now we just test this model and try to apply it to our case. Over here, we have mapping of this model for random distributions. You see over here, you have effectively electrically uniform shells. You are given the core, and you are given different thickness of the shell. And here you have the shell, fixed shell, but different radius of the course. You see, the agreement is surprisingly good. Even more, over here you have, again, testing of this model for electrically homogeneous shells with Gaussian conductivity profile. And again, you see this agreement is pretty good. So that gives us some basis to extend this model further. So what do we have? We can apply this model to random distributions. When we apply this model to the random distribution, we just should identify the parameters of these models. What is interesting, we can find, we have this equation, we can determine the percolation threshold. This is the percolation thresholds in the system of penetrable shells. So you just have this equation, you set the conductivity of the matrix is 0, you have quadratic equation, and you find the solution of this equation. And you have two solutions, actually, one is trivial, and the second becomes non-trivial at some percolation threshold. So you have the condition to find this threshold. And then you have another percolation or double percolation. This is a percolation in the system of hard cores. I want to emphasize that we suggest you have a matrix whose conductivity is very low, and you have some interface with rather high conductivity, and you have the core, conductive core. So over here you have different dependence of the concentration of the percolation thresholds upon the relative thickness of the shells. Over here you have behavior of this conductivity, and what is interesting in our model, effective critical exponents are not universal. We show this, they depend on the processing, but they are in good agreement with experimentally obtained values for paraffin-based system with metallic and semiconductor enclosure. So this is a model. Why I am talking about this random distribution? Because this is a case to test this model. So this gives our good reasons to apply this model to segregated distribution. So what do we have over here? Again, first you have the structure. You have the structure. Sorry?
You have a couple of minutes to finish because we are a little bit.
So I'm finishing. So you have a structure by optical images. And over here we have different models. So we identify low concentration. You have polymer globules. You have shells filled with globules and particles and polymer. Then when the shell fill the medium, you have some limiting case of this structure, and finally you have particles embedded into the polymer. So we just identify the parameters of the model and obtain different expression for the conductivities for this different model. So the result is that we identify the percolation threshold, we find expression for conductivities. But what is very important to emphasize that in experiment, we usually have no idea what is phi and what is C as function of C1. So actually, to finish this, to complete this model, you have to add some additional suggestion, and the additional suggestions that we use so-called alpha model for the shells. Alpha models for the shells is just some mixing rule for the shells, coarse and metallic particles and the shells. So alpha is a parameter with ranges from this. So analysis reveals that we can find the critical percolation threshold in terms of the conductivities and apply the formulas obtained before to describe different parts of conductivity. So over green function, this is low concentration, this is before percolation threshold, this is part after the percolation threshold, and this part is for very high concentration. So if you combine these parts together, you see you have a pretty good curve which describes the conductivity in the entire field. So the conclusion is what? Our model is capable to recover experimental data. It is based on the Campo group approach and in combination with so-called alpha model from soil physics. And we obtain explicit expressions, and testing theory reveals good agreement. That's it.
Okay, thank you very much. The time for 1 or 2 short questions, please.
I can see question in the hall, but I see the question in the chat.
Okay.
In chat?
Yes, in chat we have a question. Is your approach applicable for below percolation threshold range? If so, did you try to check mode hopping conductivity? Thank you for your presentation. It was a question from Victor Kisluk.
No, we didn't try it. Yes, we didn't try it, mode hopping conductivity, but actually our theory is macroscopic. I'm not sure it can be applied to this microscopic theory, you understand?
Okay,
But
thank you.
We have to consider this.
Mhm. Okay. In the hall also was some question?
No question.
Not? Okay. Okay.
We
Thank
didn't-
you. Thank you, Professor Sushko. And now the next reporter, Dr. Tatiana Barlas from the Lashkaryov Institute of Semiconductor Physics of the National Academy of Science of Ukraine. Please, floor is yours.
I'm here. Hello.
Yes. Okay.
Is all okay?
Yes. Yes. You can just make full screen. Yes. Now it's full screen.
It's okay?
Yes. Yes.
Hello to the audience. My name is Tatiana Barlas, and I am so grateful for having the ability to present you our work titled Porous Indium Phosphide, Gallium Arsenide, and Gallium Phosphide, Optical Characterization and Perspective for their use as the base for nanocomposites. Our research was done at the Institute of Semiconductor Physics in Kyiv. My presentation contains as finished research as research still in progress. Talking about the porous media, it should be noted that there are a lot of porous materials around us, including porous metals, porous semiconductors and dielectrics, porous ceramics, polymer foams, etc. Biological objects contain surprisingly many porous media, such as bone, skin, wood, and so on. Such a wide spread of biological porous structures as a result of evolution brings us to the idea that such media may hold many advantages. Of course, the methods of creation of porous materials depends on their nature and are very varied. There is a star among porous semiconductors, and it is porous silicon. Owing to its white luminescence, discovered a few decades ago, it brings main attention to itself. In comparison to silicon, 3' semiconductors are not as well investigated for now. In this presentation, we are discussing 3 compounds of 3' semiconductors whose porosity is made by electrochemical etching. A scheme of an electrochemical cell is presented on the slide. The main parts are the working electrode and platinum counterelectrode. Of course, the real experiment setup looks different and can contain more parts. Need to note that the electrochemical cells can be used for both the etching and the deposition. The pore formation process is described by the formula that is shown on the slide. Usually, for an efficient flow of the process, illumination is used. 3 types of pores can be generated in semiconductor compounds: current line orientated, crystallographically orientated, and pores, sometimes named fractal pores. Many factors affect the process of anodic etching and correspondingly the morphology of porous layers produced. Crystal surface orientation, free carrier density, electrolyte composition, temperature, etching regime, current density, etc. In the process of the development of technology, there was a move from chemically aggressive electrolytes to gentler ones up to neutral. In this work, we obtained porous layer by electrochemical etchings of N-type gallium arsenide, indium phosphide, and gallium phosphide single crystals with different free carrier concentration and surface orientation 100 and 111. Water solutions of different acid agents such as hydrochloric, hydrochloric, and sulfuric acids, mainly in the galvanostatic regime, were used. Kindly pay your attention to the method that allows to create the layers with very different morphologies and porosity. This and the next slides contain images obtained by scanning electron microscopy. At the bottom rightmost image, we can see the results of etching with ill-adjusted conditions. The technology in question
enables the preparation of both quasi-ordered and disordered porous layers of essentially different morphology, with layer parameters varied in a very wide range. Porosity was from a few to 70%. The diameter of the pores was in the range from 50 to 200 nanometers, and porous layer thickness is in the range from 5 to 90 micrometers. We can see the porous indium phosphate layers are partially ordered system of cylindrical cavities or embedded tetrahedrons, demonstrating a horizontal plate correlation between neighboring pores. Of course, this is not a so strongly ordered structure like porous alumina, but exactly indium phosphide demonstrates the largest ordering. Far infrared spectral region is very attractive for the characterization of porous polar semiconductors because, unlike well-studied porous silicon for polar semiconductor compounds, the specific region of the Restracland band and also mixed plasmon-phonon mode in doped materials exist. For our samples, we investigated specular reflection that is traditionally enough and attenuated total reflection with consideration of phonon and plasmon-phonon surface polariton excitation. It should be noted that there is still no general and correct theory allowing us to predict the optical properties as correspondingly to solve the inverse problem based on knowledge of the microscopic structure of complex composite systems. To describe the optical properties of porous semiconductors as one of the kinds of composite media, one can use the theory of the effective medium, in the context of which the complex effective dielectric permittivity is calculated with allowance for the microstructure of the composite, volume fraction of the components, and their dielectric functions. For correct application of this theory, the geometric dimensions of the components of the composite must be much less than the light wavelengths. In the vicinity of the Restracland bands of the semiconductors, this condition is satisfied very well because the dimensions of the pores and skeleton are hundreds of nanometers at maximum, and the wavelength of light in the air in this region is tens of micrometers. Thus, the calculation of the specular reflection and attenuated total reflection in this region on the base of the effective dielectric permittivity is completely correct. For Raman scattering, this condition is satisfied considerably worse, but even here, one usually obtains sufficiently reliable results. Numerical calculation and experiments were carried out for 3 typical and ubiquitous semiconductors, which are very close crystallographically but significantly differ in bond ionicity, in the structure of electron energy bands, direct to indirect, etc. Nevertheless, the dielectric permittivity of these materials in far infrared range is defined by the same widely used expression that you can see on the slide. Here we took into account the contribution of oscillation of the crystal lattice in the single oscillator model and the contribution of free current carriers in the Drude model. In a typical case of non-correlated phase, there are 2 most general kinds of composite topology, matrix and statistical. These cases are described by Maxwell-Hartley-Brueggemann formulas respectively. The quantities Lg are the so-called depolarization factor that is determined by the shape of ellipsoidal particles. In the next. Here you can see the results of the numerical simulation of these 2 models using realistic parameters. Attenuated total reflection spectra were calculated in geometry, which scheme is presented on the slide. As we can see, in both models, porosity significantly affects the shape of the spectra, but it does so in different ways. The next three slides present the experimental spectra with fitting covers made in the isotropic Brueggemann model. Here we can see the depletion of porous layer of biofree carriers. In this case, gallium phosphide bulk crystal was of phonon type, therefore we don't see depletion. At the same time, restructuring band is changed significantly. For the gallium arsenide, we see generally the same picture. Need to note that attenuated total reflection spectra are changed more significantly, and also their fitting covers are more sensitive to the changes in fitting parameters. The results of the fitting show that the frequencies of TO and LO phonons don't change it. Also, they prove the depletion of porous layers by free carriers. Reasonable and correlating porosity values were obtained. Most interesting is that the phonon damping values were changed not so much. In this case, we can say that the skeleton is a good monocrystal. If we can create a good skeleton, therefore it is a natural wish to fill it with something interesting. We can do it in the same electrochemical cell, even without the sample extraction. We change the polarity of applied voltage, plus and minus. Also, we fill the cell with electrolyte containing the aurum salt solution. Depending on deposition conditions, we can obtain various nanocomposites on the base of porous semiconductor. The images of obtained structure are presented on the slide. It should be noted that there are various techniques to embed metal into the pores of the semiconductors. Publications of other research present the possibility of metal rods and tube fabrication, for example. For our structures, we see deep penetration of gold into pores, which is also confirmed by the results of element analysis. The existence of even a small amount of metal in nanocomposite may significantly influence its properties. As an example, on the slide are presented the luminescent spectra. On the next slide, the results of micro-Raman mapping of the cross-section of the porous indium phosphate layer 111 surface with embedded gold nanoparticles are presented. As a result, the incorporation of gold nanoparticles into the pores leads to the increase of the Raman signal of TO and LO modes, especially in the 2-phonon band region. Talking about the conclusion of further research perspectives, we can create good quality porous structures. Those optical properties can be described in the effective medium model frame. Surface polariton spectroscopy shows much promise for porous composite medium characterization, since surface polariton are very sensitive to the essential parameters of porous semiconductor layers, such as porosity, symmetry, free carrier concentration, thickness, etc. The usage of these porous layers as a skeleton to create composites with organic and inorganic components seems perspective to us. Thank you for attention. My pleasure to answer your question.
Okay, thank you for the nice report. And we have time for one or two short questions.
Yes, we have one question in the hall. One moment. Two questions.
May I ask a question?
Thank you for your nice presentation. I have one very simple technical question about your setup for electrochemical etching. From the scheme, it was not clear whether your sample is anode or cathode or...
Thank you for your question. Of course, it is only a scheme. In reality, no, the very simple electrochemical cell is cylinder. In the bottom or in the top or in the side, you press your sample. a platinum counter electrode, maybe comparison electrode, and maybe something rotation or flow of this liquid. There are many construction of the cells for fabrication, for laboratory. If you have the question about our cells, I can show you.
Okay, the next question
Yeah, one more question.
online. Yes, okay.
May I ask question?
Yes, yes.
I sent
Please.
in chart reference to the
Mhm.
particle about the effective permittivity of system of anisotropic particles. So I saw this effective formula which use so-called depolarization factor, but this is purely one particle approach. So maybe this article will be helpful for the reporter.
Thank you for your question. You are right. It's
In the chart, you have reference to that particle.
Sorry, I don't see chat now. Of course, what is the model of effective medium is a question, because we have not ordered but quasi-ordered system. As we see an image, we understand that is not isotropic, but in reality, no, the result that I can show now is isotropic. Of course, they need further research and maybe another model. I try different models, and I will be grateful to discuss with you the possible.
You just look up this article, maybe you find it useful, because this is many particle approach using the same method I just reported for these systems. Maybe you find it useful.
I thank you. I remember your reports from not only today, but from previous conference. Of course, it's very interesting for us. I try to to compare theoretics and real samples.
Okay, thank you. The question was understandable. And also one more question in a whole.
Could you please explain why is it gold nanoparticles that were selected as the most convenient plasmon active component for nanocomposites?
Sorry, can you repeat the question? I don't understand and don't hear enough. Well, good.
Why you use the gold nanoparticles as
Why exactly gold rather than other metals?
Because gold is more traditional for us. I have samples from with the using of another metal, but in gold we have a good plasmon, and the plasmon in gold our nanoparticles is well investigated. You're right, Nanomaterials is the next stage. What's the metal you proposed?
Thank you.
Okay, thank you very much. And now we are finished this part of session, and we have a break for the coffee, and we will meet again at 11:30, I think. Okay?
Yes, thank you a lot, Leonid, for moderation of the session. And short information, we will have one more photo, common photo, because today we have a lot other people who come today morning, and please come on the here on the center of our hall, and we will make new photo.
Okay, see you after the coffee break, okay?
Перві три пробні. Кажу, перві три пробні.
Це фізики, тут зараз полурозпад почнеться. Ура, ура. Теперь у меня есть фотография прямо у меня на телефоне, мне надо сегодня. Я на смотрю. Сонечко. Сонечко, да. Зараз нас перефоткають. Ага. Сейчас, видите, да, он больше.
Yeah.
Давай. Ага. Добре. Ага. Давай ще так. Добре. Давай.
Мгм. Ага. Добре, ну зараз почекаємо, поки він підійде.
Що ж у нас з цією? Ага, з рюкзаком. А що ви сумки переходите?
Гарно. Добре, давай так. Ага. Ага. Так можна. Я типа розмовляю там щось таке. Ну, не важно, яка різниця. Так, зараз ми попросимо, щоб нас сфоткалося нормально. Давай. На фоне заставки, да. Видишь, и Васечку пошли. Вид, и Васенки пошли, чтобы не плачу. А, знімає, да, я поняла, я ж не поняла. Добре. Тоді зараз ще можна пульт взяти. Пашу я з пультом. М? А, так? Ага, добре. М. Ага. Ага, добре. Добре. М. М. Добре. Ага. 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 Супер. Все? То, мабуть, вже все, да? А? Рід не чую. Чуєте? А. Там не дуже я так прислухалась. Все. Добре, дякую. Так, я буду, що я так дивлюсь, типа, в зал, чи, ну, як скажете. Ага, добре. А що ще не було? Угу. Угу. Куди? Угу, угу, угу. Добре. Добре. Угу, угу. Добре. Поняла. Угу. Добре. Угу. Добре. Да, я поняла, зрозуміла. Угу. 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 Добре. От зараз так буде краще, якщо буду туди дивитись, буде краще. Давайте отак. Отак? Ага, да. Добре, я буду щось розказувати, якийсь гарний анекдот можу розказати. Отак буде, да. Ну, я зрозуміла, що це буде добре, коли ми щось розкажемо цікаве. І що там у нас? Дякую вам. Добре.
So, should we start now or what about organizing committee? Just they still have this coffee break poster, therefore I just asking. Agnieszka, you are ready, yeah?
Yes, I'm ready. Can I share? my
Yes, maybe we can try. You can try to share your
Okay.
presentation.
Let's wait 5 minutes.
Okay,
Okay.
let's wait.
My presentation is visible now?
Yes, I see it.
Okay, so I will leave it.
Yes, okay, let's wait for 5 minutes more, okay? Mhm.
Okay.
Dear colleagues, we may start our second part.
Okay, so we are returning back to the section Nanocomposites and Nanomaterials after coffee break. My name is Leonid Dolgov. I am from University of Tartu, Estonia. And our next reporter is Agnieszka Marianovska from University of Angers, France. Please, floor is yours.
Thank you for introducing me, first of all. My name is Agnieszka Marianowska. I'm a PhD student at the Nicholas Copernicus University in Toruń in Poland, but also in the University of Angers in France. My PhD topic is about perovskite and nonlinear and photovoltaics effects in perovskite thin films. But today, during the presentation, I would like to share with you some information about argon encapsulation, safeguarding perovskite thin films from degradation. So let's start. Okay, so first of all, today I would like to present you some basic information about materials which are described, which I will describe. About their properties and application possibilities. Later, I will move into measurements and results. And in the end, I will show you some summarization. Okay, maybe let's start from here. This is on the top, this is the perovskite crystals. And below, you can find perovskite thin films. Generally, perovskite crystal have got a dark color, and they can occur in natural environment. But also, we can create perovskite thin films by chemical synthesis, by other physical methods. And perovskite thin films have got dark color also. Usually this is dark brown, but sometimes it's happened that also we can create perovskite which have got orange color or dark yellow. About perovskite materials, I can say that perovskite has got enormous potential to photovoltaics application, but also we can try to use perovskite thin films in nonlinear optics. A general chemical structure of perovskites we can describe as a ABC3 formula, where A is metal cation, B metal ion, C anion. As I told you before, perovskite can occur in the natural environment, but also we can try to make perovskite thin films by chemical synthesis in the laboratories. Thanks to excellent perovskite properties, they found application. We can apply perovskite in photovoltaics in photovoltaic solar cell as a photoactive layer, and also it is possible thanks to linear absorption of perovskite thin films in the range from about 300 nanometers till 800 nanometers usually. But thanks to this, that we can obtain perovskite thin films by chemical synthesis, we can manipulate their properties, because we can choose A, B, and C part in perovskite structures. Thanks to this, generally perovskite, they are characterized by linear absorption in this range, as I mentioned, from 300 nanometers till 800 nanometers. But we can change this range a little bit because we can change ABC parts in perovskite structure. So let's say that perovskite have got a tunable band gap also, and the first perovskite photovoltaics possibilities was discovered in 2009 by Japanese scientist Kojima. And this guy, first time, he created as a first person photovoltaic solar cells with perovskite thin films, and his photovoltaic solar cells achieve efficiency about 3%, and every year efficiency of perovskite solar cells increase year by year, and nowadays we can find perovskite solar cells with efficiency about 29, about 30%. So if we want to compare perovskite solar cells efficiency with silicon ones, we can say that perovskite has got really big potential, because nowadays silicon solar cells has got efficiency about 20%. About 10 years ago, someone also noticed that perovskite thin films, they are characterized by nonlinear absorption. So we can use perovskite thin films in nonlinear optics also. From the economic point of view, perovskite thin films, we can create them and we can spend not too much money for their fabrication. So here I put information that perovskite, they are also low-cost fabrication. As application, the most common application of perovskite thin films is in photovoltaics as a photoactive layer in solar cells, but we can use perovskite thin films in lasers, in optical computing, in image sensors, as a photodetector. We can create light-emitting diode also. Recent researches about perovskite, they are focused mainly on photovoltaics, on the nonlinear optics, but also a lot of researchers focus on stability of perovskite thin films, because they are unstable, and this is the main disadvantages of perovskite thin films. Despite the enormous potential of perovskites, the commercialization of perovskite devices is still impossible. The reason for this is the instability, as I told you. And here I put some photos of perovskite thin films, which I did by atomic force microscopy measurements. And we can see that the first on the left photos is I made directly after receiving my perovskite thin films, and the other one photo I made after 6 months about. And what we can see here, that after the 6 months, the perovskite thin films, let's say, completely disappeared. Why? Because perovskites, they are sensitive for external, but also they are sensitive of external and internal factors. The external factors include all stimuli coming from the environment, such as humidity, high air temperature, lighting also, but internal factors include the ion migration, thermal phase, and chemical stability of the And my question is how we can improve perovskite thin film stability, because for me, in my opinion, it's a really important topic if we are planning to use perovskite thin films in real devices, optoelectronic devices. My proposal is storing perovskite thin films in a dark place in an argon environment. And in this work, I examined 2 hybrid perovskites with chemical formula CH3 NH3 PbI3. It means that this is perovskite with methylammonium iodide and with lead iodide, and the other kind of perovskite is perovskite which I created from methylammonium bromide and lead bromide. Of course, I measure properties, transmission spectroscopy properties and atomic force microscopy properties immediately after received my perovskite thin films and after 1 month. First of all, we can see photos of my perovskite thin films, like immediately after received and after 1 month. Perovskite with lead iodide was dark in the both case, and perovskite with lead bromide was orange also. And we can say that by eye we cannot notice any differences. I want to mention also that to create my perovskite thin films, I used method which is called physical vapor deposition, co-deposition process, exactly. Thanks to co-deposition process, I can create new material. Which has got different physico-chemical properties than materials which I have got at the beginning of this process. For example, I create the first one perovskite from methylammonium iodide and lead iodide. What this mean that I put here into one source methylammonium iodide, and to second source I put here lead iodide. Later I start to heat both of materials and they start to evaporate. Exactly, this is sublimation process, and they start to settle on the substrate on the top of the vacuum chamber, because all process it's happen in the slightly tightly closed vacuum chamber in high vacuum pressures, under high vacuum pressures. I measured spectroscopy, transmittance spectra for both of these perovskites. And also I checked structural properties by atomic force microscopy method. And I checked also nonlinear third harmonic generation for this perovskite thin films. Okay. What about transmission spectra, which I got for both kind of perovskites? I did this perovskite in composition 1:1. It means that they consist of 50% of methylammonium iodide and 50% of lead iodide, and in the other case, 50% of methylammonium bromide and 50% of lead bromide. And the transmission spectra of these thin films recorded immediately after receiving the layers and after a month are characterized by a very similar course, as we can see here on the picture. The general character is preserved, but differences are still visible. In both cases, transmission decreases over time. And more significant differences in the recorded spectra are visible for the perovskite with lead bromide. It can be concluded that after a month of storing perovskite samples in a dark place surrounded by argon, they slowly degrade. Another things which I did, it was atomic force microscopy measurements and analysis. I focus here on the Minkowski functionals analysis, and I focus on the high distribution and medium roughness and average crystallite height. And analysis of atomic force microscopy measurements of both perovskite thin films shows that all surfaces are covered with evaporated materials, and there are no penetrations into the substrate. The surface topographies of both layers measured immediately after receiving them show that the layers consist of small numerous crystallites of different heights distributed slightly unevenly over the entire tested surface, what is visible here on the first photos. The more homogeneous is the perovskite with lead bromide, which is confirmed by the more symmetrical distribution of crystallites height. And also it's visible on this chart, like immediately after receipt, we have more symmetrical shape of chart, and after 1 month, the green one, it's less symmetrical. So it's confirmed that that at the beginning, the uniformity of perovskite, this kind of perovskite thin films, was better. After a month of storing the samples under argon in a dark place, the atomic force microscopy topography of both layers becomes slightly less uniform, and single bigger and higher crystallites appear, making the total average roughness of the layers almost twice as high as that calculated immediately after receiving the samples, which I put this information here as a medium roughness, and medium roughness is more or less twice time higher than at the beginning. They are single. We can observe here after 1 month single penetrations into the ground, and Minkowski functionals graphs confirm the above statements. The shape of Minkowski volume function in both cases confirms that the layers undergo slight degradation over time, and the Minkowski connectivity function confirms that the passage of the time causes the examined structures to transform into island structures. Like from the Minkowski connectivity, if we looked here, we see that immediately after receipt, the shape looks like that. This part, this volley confirms, this is volley and peak, and in the Minkowski connectivity chart, this part show that this is porous structure, and this peak, this is island structure. But after 1 month, we see that this volley is really, really small, but the bigger one is, the peak is bigger one than this volley. So it's mean that after 1 month, the structure of the thin films of this perovskite change character to the island. Like they created rather island than porous structure. And the situation is more or less similar, let's say, in the other one case, like Minkowski connectivity, blue chart is more symmetrical, and the valley and peak is higher and deeper, let's say. But after 1 month, we can see that valley and peak, it's smaller. And I checked also nonlinear optical properties of both perovskite thin films. On the left side, this is for perovskite with lead iodide. On the right side, this is for perovskite with lead bromide. The third order harmonic generation, how it looks like and how it's changed immediately after receipt and after 1 month of storage perovskite in an argon environment. To do these measurements, nonlinear optics measurements, I used a laser with 30 picoseconds laser with wavelength 1064 nanometers. I put my samples with thin films here on the rotational table, and thanks to photomultiplier tube, I could check third harmonic generation signal and compare of results after calculation. For the calculation, I used Kubodera-Kobayashi model, and in this model, I can calculate third order nonlinear susceptibility. This is key 3. I can calculate this parameter thanks to, and I in this Kubodara-Kobayashi model, I compare my results with reference material. For third order nonlinear susceptibility, the reference material is silica. And I put silica in the table because for silica, for the reference material, third order nonlinear susceptibility is equal to. And in this Kubodara-Kobayashi model, I use some parameters and I compare my results with reference material. And thanks to this, I can compare results. So what we can see here in the table that for perovskite with lead iodide, the third order nonlinear susceptibility is about 25. And after 1 month, I got results about 10. And in the case of perovskite with lead bromide, the third order nonlinear susceptibility is about 55, and after 1 month, 12. So we can say that after storage this perovskite, 1 month storage perovskite in argon environment, the third order susceptibility decreased about more than twice maybe, but still they are useful in nonlinear optics, because if we want to compare this perovskite thin films and this nonlinear parameters with reference material, which is silica, and third order nonlinear susceptibility for silica is 2, our results, which I got, my values, like 10 for perovskite with lead iodide and about 12 for perovskite with lead bromide, it's still higher than reference material, because in this kind of measurements, usually, really often, the values which we can get for other kind of materials, they have got usually about 1 or less than 1 even. But for the perovskite, the value is still higher than for reference material, which is silica. So
Agnieszka, you have a couple of minutes to finish.
Okay. So we can summarize that argon environment slow down aging process of perovskite thin films, and it can be useful for storage perovskite if you want to try to apply perovskite in photovoltaics devices, in the optoelectronics or nonlinear optics. So to summarize, I can say that hybrid perovskites are very sensitive to external conditions, especially for high humidity, and finding an effective way to protect perovskite thin films against the negative impact of the external environment will be groundbreaking in the field of photovoltaics and optoelectronics. Let's say that proposed way to slow down the aging process of thin film layers, perovskite thin films, is to store them in a dark place in argon environment, and it's useful, and the argon environment slow down this aging process. And storing perovskite thin films in argon environment in a dark place slow down the aging process, but however, they have a significant impact on nonlinear optical properties, parameters such as third harmonic generation. And thank you for your attention today.
Okay, thank you for the nice report. And now we have time for one short question.
Can I ask a question?
Yes.
Kyiv National University, Sujuk. Very beautiful research in details. I have a question about recent news in mass media about that Japanese people has invented some covering for materials that are degrading very quickly to make such materials like perovskite. Maybe I'm wrong. Maybe you can correct me, can survive under an external environment much longer, about 30 years, in comparison with a competitor silicon plates that degrades during 10 years, that's maximum, and have a lower efficiency. You mentioned team from Japan. So your research is very useful in the context that you can save the material until new covering will be provided. Did you hear about such achievement? Thank you.
About storing perovskite in, or about make longer lifetime of perovskite, yes?
Yeah, about new kind of covering for
yes, I heard about other techniques. I choose this one with storage perovskite in argon environment, but also I heard about covering perovskite by other materials. But what is important from optoelectronic point of view, it's important to choose materials which won't affect on the other properties of perovskite thin films. For example, for these materials, which we can choose as a cover, it shouldn't, for example, affect on the spectroscopy, on the transmittance, absorbance, on the photoluminescence and other parameters. So, for example, it means that this is encapsulation, for example, by covering perovskite thin films with other materials. But also we can find, in the literature, we can find another way to protect perovskite thin films from the external environment. But it's hard to find good solution.
Thank you very much. Thank you very much. Actually, you're right, because when you cover by some material that becomes close in density
Yes.
with a surface that is active medium, you will lose a lot of properties. Actually, that is true for such a chemically and kinematically active matter like perovskite. As is shown, it becomes creating spherical, maybe because of attractive forces between particles on the surface, it becomes distributed with time with more diameter, with particle with higher diameter. That is that corresponds to the famous known law about bubbles that increase size with time. If you have droplets of some material in liquid phase around, they will create droplet with higher diameter with time. Because of higher efficiency, the droplet will have lower potential energy. Excuse me for such information surplus. Thank you very much. Thank you very much.
Thank you for your question. Thank you.
Okay. Thank you for your report. And now the time for our next report from Dr. Evgen Belyak, Institute of Information Recording of the National Academy of Science of Ukraine. Please, floor is yours.
Good morning. I'm here. Can I share my slides by now?
Yes.
Це хай заберуть презентацію зараз іншу, бо ти ж не можеш поділитися. Проси, щоб забрали презентацію. Все, можеш ділитися.
I see.
Все.
Can you see my slides?
Yes.
Okay.
But
now,
you can make it in full screen mode now.
Yeah.
Just F5. F5 button should work. Okay, nice.
So
Nice.
I'm delighted. I'm delighted to be here to talk with you about application of nanostructured luminescent coating for photo detection optimization. So basic issue of the modern digital camera is mismatch of the spectra of photometrics elements and visual spectrum of the light. You can see basic additive color scheme here, RGB triad, blue, green, and red, and absorption spectrum of the most common photoinducer cells, photoelectric inducer cells, like monocrystal silicon and polycrystal silicon. You can see that main part of the spectrum is in the red range and near infrared range, while absorptions of green channel is twice lower, and absorptions of blue color channel is even less. It's 4 times less than red channel. Thereby, we got lower photosensitivity of the matrix and color imbalance. Of course, you can adjust colors by adjust color channels by the blue channel, but then whole photosensitivity of the photomatrix will be 4 times less. So let's see how manufacturers of modern photomatrices address this issue. On this slide, you can see most common biofilters of photomatrices based on RGB and SMIC color scheme. There are different colors, but the idea is same. It's adjusted to the human eye. It's some color of the long wave visual spectrum, some color of short wave visual spectrum, and someone in between. In one case, it's red, blue, and green in between. In other case, it's magenta, cyan, and yellow in between. In all 3 common schemes, which is RGB, magenta, yellow, cyan, and combined red, yellow, and blue, we can see the same idea. Manufacture doubles the color which in the middle, or in one case it's green channel, in other case it's yellow channel. The reason is that in solar spectrum, yellow and green is has the most intensity. So we lose our color balance, but got better contrast. And then we adjust color balance only by computer algorithms, which is the only way to solve the problem. So those schemes are not the only ones. Let's see another ones. Wait. Прибрати цю.
Нічого, просто
Нічого.
легше. Її не бачу.
Okay, the next schemes, there is not a triad, but tetrad. So four color channels. But again, we can see doubling the central channel, combination of green and yellow combined with white filter, or we may say no filter for the color channel. The idea of using white filter or raising no filter for one of the color channels is quite widespread, especially for codec photometry. The main set of codec photometrics for every the channel is doubled, so it again balance. In most specialized color schemes for Sony and Huawei, so-called quad biophotometrics filters, we again can see that green channel or yellow channel is doubled. Same here, it's for a diminution of the Mawaya effect, but again, green channel is doubled, or there are in first scheme X trans filter, there are even more than doubled. So our so you can see that we compensate less absorbance of the green channel photoinducer, but the problem is blue channel. Our idea was to make a mathematical idea, mathematical model to calculate which kind of Stokes shift by photoluminescence coating we need to make a spectrum conversion of the blue light to adjust it to the to our photocell.
Something happens with audio. I don't know. Can you correct it? Picture is okay, but audio is distorted strongly. And now it disappeared. Audio is absent. So Evgen, are you with us? For some reason connection is lost. I don't know. Or picture is frozen. Maybe we can, I don't know, we can wait a little. When connection will be recovered. Okay. So I'm asking Andrei about technical support. Andrei, do you know why we have the problem with the volume?
I don't know this speaker disappear in Zoom.
I see.
Maybe going to the next speaker.
I don't know. Let's wait 1 minute. If it will not return, then no, it's 12:15. Let's wait. Okay, 12:16. Let's wait till 12:17. If he will not return, then we can come to the next one. By the way, the next speaker is Ladislav Romanchuk from the Lashkarev Institute of Semiconductor Physics. Ladislav, are you hear me?
Yes, I'm ready.
Okay. Probably, yes, because of the loss of connection. Probably I invite Vladislav Romanchuk with the next report. It's pity that Evgen just interrupted, but
Well, do you see my shared screen?
yes, I see your shared screen.
Okay, so let me start.
Mhm.
Well, thank you for presentation, and it's my pleasure to present some results of my scientific work to the audience. So I'm Vladislav Romanchuk, a PhD student of Lashkarev Institute of Semiconductor Physics of National Academy of Sciences of Ukraine. And the title of my report is Perspectives for the Application of Biosensor based on the Surface Plasma Resonance Phenomenon for early prediction of brain tumors postoperative progression. So, yes. So over the past decades, there has been a significant breakthrough in SPR technology in clinical diagnostics, environmental monitoring, pharmaceuticals, and polymer engineering, covering a wide range of healthcare and life sciences. The main advantages of SPR investigation are non-invasive detection and real-time monitoring of various binding events. Furthermore, the SPR detection allows direct measurement of affinity and kinetic constants of biomolecular interactions and doesn't require specific fluorescent or radioactive labeling, which prevents their binding deterioration. So the aim of the work was to develop a test that could determine the presence of residual brain glioma tissue after the resection. So let's start from SPR itself. It's a physical phenomenon that occurs when incident light excites surface plasmons. So we need a metal medium attached to the electric medium. So when the polarized in normal plane light hits the surface plasmons, then they excite. So the most convenient optical scheme for plasmos excitation is a Kretschmann configuration. So it consists of a source of light, a prism of total internal reflection, a thin metal film is a sensitive element covered with sensitive layer, which is attached to sensitive layer or to investigated medium. So it can be both or gaseous or fluid. And the intensity of reflected light is measured by a photodetector. So this scheme works on disruption of total internal reflections. So on the corner picture, you can see how the intense transmits from light to plasma excitations, oscillations. So on this slide, Plasmon 6 device is shown as well as its optical scheme. So it's using a Kretschmann configuration, but also the prism can rotate. So we measure the intensity of reflected light for different angles. And the minimal point, the minimum of intensity of reflected light is also maybe called a SPR angle. So this setup depends heavily on the material of prism, material of substrate, on the metal of sensitive element, on its thickness, and in case if there are some changes of refractive index of medium in the flow channel, which may be obtained during substitution with different medium or while some molecular interactions on its surface, then it leads to shift of the SPR angle. So this shift would be called an SPR index. So the purpose of this work was to develop a test to determine completeness of resection of tumor tissue in brain using indicators of level of aggregation of blood cells with SPR device. So here is shown our setup for investigation as sensitive element. A thin gold film was used with thickness 50 nanometers. Prism and substrate were made of glass optical. So blood cells are flown through the flow channel using a peristaltic pump. And here you can see that flow channel is attached to sensitive element so that blood start aggregating here, and it influences the behavior of surface plasmon waves. So let's take a closer look at the surface of sensitive element. In case of healthy blood cells, they aggregate in such way that cover the majority of surface. And the lower picture is more accurate in terms of scale because blood cells are measured in microns, while plasmon waves penetrate up to half of a wavelength of light. So if we're using red light with wavelength 650 nanometers, then they penetrate half of that value. So in case blood cells cover the majority of surface, then we obtain higher response of measurement. But if blood sample was taken from a patient with some diseases like brain glioma in particular, then the cells are pre-bonded before aggregation, so they cover much less space, and the response is much lower. So during our investigation, we compared blood samples of patients with different grades of malignancy of tumor before resection and 7 days afterwards, and compared the results. So as you can see from this table, what we obtain. In case of complete resection, so that no residual tissue is left, then SPR indices decrease after resection. Is the case for all grades of malignancy. But otherwise, if resection was incomplete, then SPR indices increase after resection. So it may be concluded that this method will allow to determine glioma metastasis soon after the resection, and as well as any time afterwards. Secondly, this method is unique because it differs in availability and speed and doesn't require reagents or radioactive labels. And as it's label-free, then it may be used for the development on other types of tumors. So that's all for today, and I'm ready to clarify any questions.
Thank you for your interesting report. I have a question. Did you use a washing in your procedure? It means that when you deposit the sample, you measure, then you deposit another sample. You need maybe some to wash previous one, or?
Well, as you can see from this picture, gold film, the sensitive elements are changeable. So that's not the case.
I see. Okay, thank you. Other questions? Are there any other questions? So if not, then thank you for your nice report, and we just come to the next speaker.
Wait a moment.
Okay.
Thank you for talk. And the question is, what about selectivity of your method? Because it looks like any problem with blood coagulation could break this mechanism, and your diagram, you could not selectively define your problem, your disease.
Well, thank you for your question. I understand you. In general, the surface of sensitive element may be covered by different ligands for selectivity. But in case of this investigation, why I mentioned only residual tissue, so that this method is used for special target group. They know that their main disease is glioma, so that we just neglect our reasons, like different traumas or etc. for problems with blood aggregation.
Okay, thank you.
But another application of this method may be used for healthy people, and if we obtain any anomalies in aggregation levels, then we may suggest using another methods to find the reason.
Okay, thank you very much again. And our next reporter is Dr. Anton Kostetsky, yeah?
Yeah.
Okay, floor is yours, please.
Can you hear me? Sorry.
Institute of Physics, National Academy of Science of Ukraine.
Okay, thanks.
Yes, you can start. We cannot see your presentation at the moment, so you need to share it.
Okay. I try. And then?
Maybe we need to wait a little bit. I see that sharing is started, but the picture is absent for some reason. I don't know. It means that you should select correct program for sharing or correct window. The same result. Another variant, I can ask our colleagues at place, if you send your presentation to them, they can open for us and just maybe by such a way to proceed. Or your variant, you can just save it in PDF form and try to share PDF. Maybe it will work better.
Okay. No, I think I'm doing something wrong. Sorry.
Andrei, do you have the presentation on your side?
Going to the next speaker and then
Okay, let's do so. We just make just substitute. You just try to solve the technical questions. Let's go to the next speaker. Speaker, it's
I'm so sorry.
no problem. You can just try to solve it. Dr. Oksana Kostev, Ivan Franko National University of Lviv. Are you with us, Oksana?
yes, he here.
Yes, okay. The floor is yours. And then Anton try to solve the technical problems.
Can you on my presentation?
Oksana, we hear you, but in Zoom, I don't see the picture. I don't know why.
I wait for my presentation.
I see. Okay.
Good.
Let's wait a little.
My presentation, our researcher of the preparation of new microparticles contain of transcarpathian clinoptellulite and the different approaches ways to use their functional activation. This study is important due to the broad range of application of clinoptellulite and in environmental and biochemical fields. Particularly, its role is in detoxification, adsorptions, and catalysis in variety chemical reactions. Our main goal was to explore how to different treatment and modification can exchange the functional properties of clinoptellulite. This investigation will provide with our colleagues from Institute of Sorptions and Problem of Endoecologies and Institute of Cell Biologies. For our investigations, we use the clinoptellulite from the Sokornica deposit in the Zakarpattia region of Ukraine. This particular clinoptellulite knows for its high purity, contained 85–90% of main components and belong the low silica calcium variety. Its structure is free from clay impurity. Natural clinoptellulite offers several advantages over the other sorbents. It's resistant to aggressive media, thermal stability, and mechanical strength. This clinoptellulite is one of the natural zeolites that can be used for medicine. Additionally, it can be easily modified and regenerated, which is critical for its repeated use in industrial and environmental applications. Its high sorption capacity, combined with a well-defined pore size, make it ideal for adsorptions both of inorganic and organic substances. For create of novel microparticles, we use two ways to prepare of them. One of them is use the solid phase extraction in dynamic condition. Another way is to create microparticles by mechanochemical treatment. The sample of clinoptellulite with silver or copper substances. We subject these samples to mechanochemical treatment with a planary ball mill, which involved varying speeds and duration. This process allowed to produce different forms of clinoptellulite with modified extraction and enhancing functionalization. The X-ray diffractions and scanning electron microscopy studies revealed the mechanochemical treatment significantly altered the structure of clinoptilolite. Initially, the diffractogram of natural clinoptilolite shows distinct peaks corresponding to clinoptilolite and alpha quartz. However, with mechanochemical treatment, especially in high-energy meal, the peaks gradually diminish and the crystal structure become amorphous. This process is more pronounced with intense and probably milling, particularly in dry condition. Some images show that natural clinoptilolite has a graduated structure with particular range from 200 to 500 micrometers. After mechanochemical treatment, these particulars break down into smaller irregular shapes that form agglomerates. The adsorption properties of clinoptilolite were improved through the acid treatment, which increased the specific surface area by removing cations that blocked micropores. Doping the clinoptilolite with metals further altered its porosity, increased the absorption volume, particularly in the microporous range. This is crucial for application where high surface area and intense absorption properties are needed. Natural clinoptilolite is micromesoporous materials, but its micropores are often blocked by cations like potassium, sodium, and calcium, limiting its absorption capacity. The nitrogen adsorption-desorption isotherms we obtain correspond to mixed type 2 and 3 isotherms. After converting clinoptilolite from its acid form, so acid treatment, we remove some of these cations, significantly increase the specific surface area and making more micropores accessible. Enough subjects that mechanochemical treatment reduce the specific surface area in acid modifier samples, increase the overall absorption volume, particularly in macropores, which research volume of 0.2 cubic centimeter per gram. Doping clinoptilolite, especially with silver, significantly alters its pore structure. The nitrogen adsorption-desorption isotherms show more pronounced by hysteresis loop, indication in increases in mesoporosity. As silver content rises, the peaks is mesoporosity size during shift to the large size. In doped sample, mesopores contain 60–70% of the total absorption volume, compared to 45% in the undoped clinoptilolite. This enhancement in mesoporosity is due to the introduction of metal oxide clusters and particular nitrate decompositions, which improve the material's over accessibility and surface reactivity. Infrared spectroscopy revealed significant change in the surface chemistry of clinoptilolite after doping and mechanochemical treatment. This was a noticeable increase of surface OH group and siloxane bonds, which is crucial for adsorptions and catalytic activity. The spectrum also shows a shift and increase its adsorption band related to C or aluminum bonds, especially in silver-doped samples. This change suggests formations of a new active center on the surface, enhancing the material reactivity and functionalizations. The antimicrobial activity efficiency of the clinoptilolite depends heavily on these electronic properties. Doping with silver and copper cations, it shows in the spectra primarily replace silver and in the silver plus state with within cations exchange positions with minimal metallic silver present. This state is confirmed by XPS spectra, which show consistent building energy for silver plus across samples. This electronic characteristics are crucial for enhancing to materials' ability to generate reactive species and contribute to antimicrobial activity. Our study also for the morphology of bacterial cells efficiency in the antimicrobial activity of cleanup telluride. For example, presence of polysaccharide capsula Pseudomonas aquarosa significantly reduced the material's efficiency, while the peptidoglycan released in Bacillium subtilium did not have a significant impact. The results indicate that the cleanup telluride could be effective against bacterial biofilms dependent on the specific bacterial structure. In conclusions, our research demonstrates that the functionalization property of cleanup telluride can be significantly enhanced through various physico-chemical modifications, including doping with metal ions and mechanochemical treatment. These modifications improve its surface area, porosity, and antimicrobial activity. Moving forward, future explorations of this modification could be lead new application of cleanup telluride in environmental and biomedical fields. Thank you for your attention.
Thank you for the nice report, Oksana. And now we have time for a short question.
No question.
No questions. So we can come to the next reporter. Thank you, Oksana. And the next reporter, Dr. Sergei Polishchuk from Kurdyumov Institute of Metal Physics of the National Academy of Science of Ukraine. Please, floor is yours, Sergei. So we have some problem with the voice in Zoom, I think.
Voice in Zoom.
Andrei, I hear you, but reporter, I don't hear for some reason.
How do you hear me?
Now, yes. Now, yes.
This work was done by researchers from three institutes: Institute for Metal Physics, Electric Welding Institute, and Institute for Problems in Material Science. I would like to tell about phase formation in multilayer eutectic aluminum copper foils and some applications for these foils. Sorry, just a moment. We cannot. Just a moment, we cannot visualize next slide. Okay. And we will start from the end. Practical aim of the work is to try to use these multi-layer foils as filler materials for welding difficult to weld alloys. For example, it can be titanium copper or aluminum copper alloys. We can use this filler materials for diffusion welding, and it can be useful not only due to additional heating, but mainly due to modification of contact surface of welded parts that in general is useful for the welding. After welding, we have approximately such microstructure. We can see there are almost no traces of the filler foils. So, but very important, the result of this welding will depend on the phase transformation in the foils, and we need to study it. To obtain these foils, we can use electron beam evaporation from ingots, aluminum and copper, with subsequent deposition on rotated substrate. And we can obtain foils of different composition and different modulation period. Modulation period is the sum thickness of one aluminum layer and one copper layer. And of course, we can change also temperature deposition. Generally, thickness of such foils was up to 50 micron. Why we choose system aluminum copper? Just because it has lower temperatures of the beginning of phase transformation as compared with known system, for example, aluminum titanium. Moreover, we choose FTAC composition, so we have lowest melting point for such foils. What we know about possible transformation in such films? There are a lot of studies, but results of the transformation are very, very sensitive to different factors, except chemical composition, heating rate. It can be rotation relations between phases, even presence of excessive vacancies in foils, and so on. But we can summarize all this result by the following diagram. First of all, we have a stage of interdiffusion and formation of solid state solid solutions at the interfaces. Then we have formation of aluminum to copper phase. Then forms another phase, which can be different. It can be aluminum 4 copper 9, maybe equiatomic aluminum copper, and maybe aluminum copper 3. It should be noted that most popular phase, namely this. This phase forms almost the whole composition range. It should be noted that main factors studied at these different investigations, only chemical composition and heating rate. But as far as we know, nobody studied effect of modulation period on the phase composition and phase formation. So it was the aim of this work. We study the effect of the modulation period on the sequences of phase transformation, as well as studied thermal characteristics of the reaction and mechanical properties. Especially important to know plasticity coefficient of the foils. In particular, in this work, we study foils with modulation period of 15 nanometers and 1000 nanometers. So for the nanoscaled, for foils with nanoscaled modulation period, we have formation of two phases, sorry. It was phase aluminium 2 copper and aluminium 4 copper 9. It should be noted that this phase is enough complex, complicated even. It contains more than contains 52 atoms per unit cells and is considered as approximate structure to quasi-crystalline structure. For example, we can see some pentagonal motifs in the structure of the phase. At the same time, this phase forms almost at whole composition range. Study using transmission electron microscopies confirmed the formation of these phases. In case of foils with large modulation period, we had the similar phases at the early stages, namely phase aluminium 2 copper and aluminium 4 copper 2. But at higher temperatures, we were found formation of aluminium copper 3 phase. Electronic microscopy confirmed this result, and X-ray diffraction also. Moreover, we conducted additional studies using the measurement of electric resistance and temperature coefficient of electroresistivity, and also confirmed temperature of the phase reaction. That's allowed us to present the following consequences of the reaction. At the first stage for nanoscaled foils, we have formation of aluminium 2 copper phase. It can be even during deposition of the foils. Then we have formation of aluminium 4 copper 9 phase. And due to the fact that this phase, this chemical composition is metastable at high temperatures, these phases transform into equilibrium phases. That phase disappeared. For foils with a large modulation period. We had a similar picture for low stages, but at high temperatures we found formation of copper-3 aluminum phase, and after following heating, we have also only equilibrium phases. We can picture the transformation by this diagram. Obtained results allowed us to suppose that the formation of both aluminum 2 copper and aluminum 4 copper 9 phases predominantly takes place at the interface boundaries between aluminum and copper layers, and between aluminum 2 copper and copper layers, respectively. But formation of aluminum copper 3 phase presumably occurs at the boundaries of columnar-like copper grains. Moreover, it should be noted that the formation of the phase is accompanied by change in the specific volume per atom. For example, the transformation from aluminum to copper leads to decrease in the specific volume per atom, and formation of aluminum copper 3 and aluminum 4 copper 9 leads to increase the specific volume. And we can suppose that these processes compensate each other. Moreover, we should keep in mind that we have vacuum condensate, and conditions for deposition of the condensate correspond to a so-called second structural zone for models of Morchan, Demchyshin, and Thornton. That we have columnar-like structure of our condensate, of our foils. And of course, for such foils, we have texture. It's not only texture of initial aluminum and copper layers, it's also texture of formed phases, aluminum 2 copper and aluminum 4 copper 9. In both cases, we observed some texture, and we can show some orientation relations between the directions of the textures. So we have texture, initial texture 111 for aluminum and copper, texture 110 for aluminum 2 copper, and 110 for aluminum 4 copper 9. And the same situation with texture of copper 3 aluminum. We can suppose that the formation of this phase while maintaining the orientation relations with the initial aluminum and copper can lead to a decrease in the interface energy, which significantly lowers the energy barrier to nucleation and allows the appearance of very small nuclei, thus facilitating the formation of the new phase. This similar situation with the formation of phases aluminum 4 copper 9 and aluminum copper 3. So in cases when we had texture, specific texture of formed phases, we can suppose that it can facilitate their formation in comparison, for example, with non-phase aluminium copper. If we consider the structure of aluminium copper, aluminium copper 3-phase and aluminium 4 copper 9-phase, we can mention that both these phases can be considered as derivative from initial BCC phase. BCC phase has parameter 1.29 nanometers. FCC phase aluminum copper 3 has approximately parameter twice times larger, and this phase aluminum for copper 9 has 3 times larger parameter. So we can consider model of Besson. It's French researcher who proposed model of athermic transformation from FCC matrix into BCC aluminum 4 copper 9 phase. It can be considered as Bain transformation, and our results in some case confirms this possibility, and we can also confirm that it's possible that formation of aluminium copper 3 and aluminium 4 copper 9 phases was performed by Bain mechanism of transformation. Moreover, we interested also in colorimetric investigation of our foils, and we found that nanoscaled foils has approximately 2.5 times higher heat flux as compared with foils with large period, and it can be due to higher number of reaction interfaces per unit of volume. Moreover, we estimated activation energy for the formation of aluminium copper 3 phase and aluminium 4 copper 9 phases, and found that for nanoscaled foils, the energy of activation is lower. No, what about plasticity? It's a little bit unexpectedly, but nanoscaled foils was found to have worse plasticity as compared with foils with large modulation period. It can be due to significant contribution to plasticity of large aluminum grains. At the same time, changes of mechanical properties indicate about prevailing role of the grain boundary strengthening mechanism and growth intermetallic compounds in the foils is accompanied by an increase in the micro-hardness and Young modulus of the foils. I will not repeat conclusions, but just say that we investigated the phase transformation by different methods, created some simplified model of the formation of the phases and found the effect of the modulation period on the phase formation and properties of the foils. Thanks for your attention.
So, Sergey, thank you very much for your report. And now we have some small time for question.
I have a question. If you
Okay, please.
Thank you, National University of Research. I have a modest question. How did you study mechanical properties, critical one for elasticity for the foil? What is the critical width for the foil that you can pick up somehow and bend? Thank you.
As I understand, you ask about mechanical properties, yes? Yeah?
Yes, how did you investigate mechanical properties? Because what was the width of your foil? Thank you.
What is the
width? What was the width of your foil? How did you pick up it and bend? I mean, you cannot pick up a film by
even 10 centimeters if you want. It's not problem, absolutely.
So you had produced quite thick films, right? You could pick up some
films, and we have films of almost any form. It can be a rectangular form, approximately 10
okay, yes, I understand. So you have you did covering, and then disattached your foil from the basis, from substrate, right? To discover mechanical properties, or how did you do it? Shortly, into the words, thank you.
To make separation our condensate from substrate, we previously deposited salt layer, and after by etching we removed this salt layer, and we had only foil without any substrate.
Okay, we have one more question.
Thank you.
One short question.
Is your foil is stable due to temperature increasing after preparation? Because copper and aluminum have different specific heat capacity, different coefficient of thermal extension, and so on. How temperature effect on your foil?
No, it should be mentioned that we deposited our foils almost at room temperature. In fact, it was not room temperature, it was about 90 Celsius degree. It's not so high to have some big thermal stresses in the foils and after cooling. So there is no problem with this. Thank you.
So thank you very much, Sergey. And I think that now we have the break for the lunch. and we will be back at 2 o'clock or a little bit later, maybe.
We will give one more opportunity for Anton Kostetsky. Maybe he is.
Okay, okay. I just wrote to him. Anton, are you with us?
Yeah.
Okay,
Yeah,
let's try again.
I can try again.
Anton. Mhm.
Thank you. It's working now. Or not?
Unfortunately, we still don't see the screen. Probably we will have opportunity to download your PPT presentation from our mail, and we will give you a floor at the end of the next session, if you agree.
Maybe I can try in another program. Okay, okay, and I send it.
Yes, maybe from the Andrei side, we just on place we just they just download your presentation and you can just talk. Okay, okay. Thank you, and see you later. Okay. So now we have a break for the lunch. Thank you all for participation, and see you at 2 o'clock or maybe 10 minutes past 2. Okay. Thank you. Thank you very much.
Thank you, Leonid, for being a chairman of this part. Thank you very much.
Okay, thank you.
Антон, скинь нам просто на почту конференції свою презентацію, ми її для тебе розшаримо просто і будеш показати, коли переключати слайд.
Yeah. Yeah.
Слухайте, а цей слайдер не працює, може тут достатньо просто батарейку поміняти? Де він працює? Він не працює, він вечором ти ним не міг переключати. А, тобто він працює? Я хочу так, в повний ріст. Отак. Ну, щоб... Ну, для чого? Ти хочеш мене відкритим ротом перекупати? Для чого? Я коли розмовляю, в мене міміка якась дуже дивна виходить. Воно не клацнуло. Ні, ну взагалі-то правильно так. Ну, ніби пояснюєш комусь. Ні, коли так спеціально, я коли от говорю, то я ніби махаю, ну, незрозуміло, вони в мене самі махаються. А коли поставити спеціально, не поставиш. Все, Володь? Бо я ж не маю такої великої витримки, як собака. Ну, яка сьогодні отам, скільки ти їх хвилин 15 фоткав?
Hello, dear colleagues. We will start our next session. We have a little shift in the program. I should announce that Anton Kostetsky from the previous section is now available to present his presentation. We downloaded. Anton, are you ready to start?
Yes, okay. Maybe I'm last time.
We can do it.
Wanted, if you're sharing. Okay, I'm sorry. I don't know. It's don't work. Okay.
One moment, we will do it. Okay, you can see it.
Okay, thank you.
Yeah.
Thank you for your support and good afternoon, dear organizing committee, dear colleagues. Thank you for the opportunity to present my current work. My topic is photoluminescence of PCBM fullerene derivative confined in mesopore glasses. Next, please. Composites of fullerene derivatives with various polymers have been extensively used for the more than 2 decades in a wide range of applications, in particular polymer-based solar cells and perovskite solar cells containing fullerenes. Next slide, please. Solid-state system, including aerogel in which fullerene clusters are confined into the matrices, has been reported by different authors. It was found that in photoluminescence intensity increasing with decreasing of fullerene concentration, and has peaked at around 2.26 tonovolts. Was obviously blue shifted compared for the samples with high concentrations and for few mixture of fullerenes at room temperatures. This phenomena was ascribed to the quantum confinement effect. Due to this effect, nanomaterials, including quantum dots, often exhibit size-dependent optical properties. When the size of material decreases, the band gap of material increases, and this leading to the emission and absorption, which is blue shift. But comparison of the optical properties of fullerene derivatives depending on the influence of the solvents and spatial limitations remains actually. Next slide, please. So the main aim of the work is the study of the influence of the surrounding environment, solvents, spatial limitation, temperature on the linear spectral property of PCBM fullerene derivatives. We have prepared the next samples. It will be PCBM solution in acetylene toluene, PCBM in matrices from toluene solution in polymethyl methacrylate and polystyrene. And we prepared the samples of PCBM confined in mesoporous sodium borosilicate glasses with pore diameters 1, 3, 4, 10, and 44 nanometers. Original sodium borosilicate glasses were enriched in order to remove the sodium borate phase, and we obtained through porous matrices, which have structure as considered as composed from CO2 tetrahedrons connected by oxygen atoms. The samples thereafter was heated at 100 degrees of Celsius during 2 hours. The construction of PCBM in alkaline solutions was 10 to power minus 4 molars. So we used optical absorption spectroscopy, steady-state photoluminescence, kinetic decay curves, and lifetimes measurements at different excitation and temperatures. Next, please. We obtained optical absorption spectra of PCBM in different matrices. Absorption spectra in the polystyrene and mesoporous matrices remains the structures of the profile as the same original fluorine solution. So we have strong absorption in the ultraviolet region and weak absorption in visible region. Next, please. In our previously published article, we have obtained the steady-state photoluminescence of PCBM in different hard solvents with different polarity and excitation, and donor receptor complex of PCBM with natural biopolymer melanin. Next, please. We have obtained photoluminescence decay curves and decay lifetimes measurements for PCBM solutions in acetonitrile wall. So decay curves describes by mono-exponential function with lifetimes in nanoseconds time range. Next, please. Also the same features we also received for PCBM in PMMA matrix. Decay curves described by mono-exponential function 2. Next, please. So next we have obtained steady-state photoluminescence spectra in mesoporous glasses at lifetime measurements at excitation 245. But in this case, decay curves describes by 2 exponential function with lifetimes in the pico and nanoseconds time range. Next, please. Also, we have received these features for PCBM in mesopora glasses and polystyrene for comparison to CS60 by excitation at 405 nanometers. Next, please. Thereafter, we have obtained these features for PCBM in polystyrene matrix at excitation at the same wavelengths. And next, please. Thereafter, we obtained luminescence, steady-state luminescence for PCBM in mesopora glasses with different pore sizes at excitation 337.9 nanometers at different temperatures. But it was observed the blue shifting of the peaks maxima when diameter of the porous decreases. Its effect induced by the spatial limitation of size of PCBM and nano aggregates. Next, please. And finally, we received steady-state photoluminescence spectra for PCBM in glasses with different pores at 325 and 532 nanometers excitation wavelengths. So the blue shifting in the region near 500 nanometers, which relates with ZT exciton emission bands, is induced by the quantum size effect. This effect leads to the spatial limitation of molecules forming the ZT states with pore diameter less than 10 nanometers as a consequence to observed blue shifting. So next, please. In this slide is given the example of the energy diagram of PCBM electronic transition in fluoroform solution. So PCBM shows dual structured blue and red emission bands, which corresponding to emission from the ZT and monomer unit respectively. And emission band in the long wavelength side of spectra correspond with XMR emission. Next, please. So we have next conclusions. We have studied a linear spectral time domain properties of PCBM fullerene derivatives in different media, in particular in mesopore glasses at different excitation wavelengths and temperatures. We was established the parameters of photoluminescence decay course and lifetimes, and we observed blue shifting in the photoluminescence peaks maxima, which arises in the long wave side of spectra with decreasing of pore diameters and is induced by effect of spatial limitations, the size of aggregates, and the blue shifting of the peaks maxima related with the exciton emission is induced by the quantum size effect. This effect leads to the spatial limitation of molecules forming the state with pore diameters less than 10 nanometers. Thank you very much. Thank you for your attention.
Thank you very much, Anton, for a good presentation. Do we have any question?
I have a question, if you allow.
Please, please.
Kyiv National University, Andrei. You have done very interesting research on this one. As I understand, the change in size decrease amount of particles participating in interaction and making mutual electrons, for example, or some kind of exchange electrons. And that's why the difference in energy levels increases with decreasing size. You cannot assume this. At the same time, on your graphs, we can see at some pictures that 10 nanometers fullerenes have blue shifted emission spectrum at relaxation in comparison with the 4 nanometer size. I don't ask a question that. And there is a good notation done by authors that you observe some kind of quantum effects. It can be actually related also to quantum optical effects when collective decay happens. It was predicted by decay, American scientists in some papers from 90s. Sorry, 70s. And it may be concerned that you can have some collective quantum state in your fullerenes when atoms are exchanged by photons, for example, as people say, so-called virtual photons, until the system decays completely. Do you think your quantum effect that you observed have collective nature? Thank you.
Not only well understand the question, but we have, if you understand your question for which relates to the collective effect, the main result is
the decay effect can be related to collective decay that is based on the consumption of the photons collectively. Each fullerene works like a whole system, and as you say, the size change frequency, so it hints that
maybe your question
change decay time and so
on. Decay decay
okay,
luminescence.
let's ask this way. Do you think if you increase size of the fullerene, the decay time will be increasing or decreasing? Thank you.
I guess it decay is it has lifetimes more higher lifetimes.
Thank you. Your research is great. Thank you.
Thank you very much for the discussion, and thanks, Anton, once again for your presentation. We will move forward to our program. The next speaker should be Anna Dyachenko, but I can't see her in the waiting room. Anna, can you hear us? If no, we will move forward. Anna, please contact us and we will add you to the program later. The next speaker should be PhD student Mikhailo Mikityuk from the Lviv Polytechnic National University, Ukraine. Mikhailo, can you start?
Hello, good afternoon. Let me know if you can hear me.
I can hear you well, please.
Okay. 1 minute, please. I will share my screen. Okay. Do you see slides?
I can see something. If it's your slides, I see a blue screen with.
Okay, blue screen. Okay. Sorry. Yeah. Something wrong with me. Okay. Okay, now you should see slides.
Second, where I see a slide and now I again see the blue screen.
Okay. I'm so sorry for this. It doesn't work for some reason.
I can propose, if you have a problem with sharing the screen, you can download it and send us via mail, and we will share the screen for you.
Okay, give me one more try, please.
Okay, one more try.
Okay, maybe now you can see it.
Now we can see your presentation, not in full screen mode, but let's see.
Okay. Sorry for this. So topic of my presentation is superconductivity of topological insulator bismuth selenide. The aim of my presentation is to share with you the results of our recent studies about magnetotransfer properties and temperature dependencies of bismuth selenide whiskers doped by palladium. So topological insulators doped with different impurities are well known to transfer to superconductive states at low temperature. This phenomenon could be interesting for fundamental physics and for future technologies like quantum computing. I will briefly discuss the experiment, our experiment. I will outline our main findings, and at the end, we will conclude the results. So bismuth selenide whiskers doped by palladium were prepared by chemical vapor deposition method in a closed quartz reactor. We used bromine as a transport agent, precursors of bismuth and selene and palladium have been loaded in corresponding ratio to obtain whiskers. Palladium impurity was used for initiator of the whisker growth according to vapor liquid solid mechanism. The reactor was situated in horizontal furnace with a temperature gradient from 800 Celsius to 480 Celsius. The whisker diameter ranges from 20 to 30 nanometers and length approach to 2 millimeters. For our experiment, we used two groups of N-type bismuth selenide whiskers with different impurity concentration in the vicinity to metal insulator transition from the metal side. Impurity concentrations and resulting resistivity you can see on the screen. So we have two samples. Pictures of the samples you can see also on the slides. The electrical contacts to make measurements were welded have been developed from platinum microwire with diameter of 10 nanometers. In order to have low temperature measurements, we used helium cryostat. Samples were loaded into cryostat and cooled down to temperature 4.2 Kelvin. In order to obtain temperature 1.5 Kelvin, the cryostat has been pumped. So overall measurements have been performed in the temperature range from 1.5 to 77 Kelvin. The effect of magnetic field on the whiskers were studied using the bitter magnet with induction up to 10 Tesla and scanning time 1.75 Tesla per minute. The temperature dependencies of the resistant for bismuth selenide whiskers with different doping concentration, but in zero magnetic field, you can see in the figure 1. Here we have few interesting peculiarities. The first one is a sharp drop of the resistant at temperature below 5.3 Kelvin. Also, wide minimum of the resistant is visible in the temperature range from 20 to 25 Kelvin. The maximum condo effect was observed for whiskers with bigger resistivity, so with less impurity concentration. So deep minimum is visible in the range from 20 to 25 Kelvin. Increasing the impurity concentration, we can observe attenuation of condo effect. In the figure 2, we can see transverse magnetoresistant results of N-type bismuth selenide whiskers in the temperature range from 4.2 to 77 Kelvin, and magnetic field up to 10 Tesla. There are two interesting features of the whisker magnetoresistant. The first one is abnormal resistant upturn at temperature 4.2 Kelvin. You can see it in the upper inset of the figure 2. We assume that this upturn is caused by appearance of superconductivity of samples. Second interesting feature is that on the temperature dependency at magnetic field 10 Tesla, wide minimum of the resistance is clearly obvious in the temperature range from 25 to 30 Kelvin. Having this info, so despite we have a big magnetic field, 10 Tesla, interaction of conducting singlet electron and localized by impurity electrons is strong. So magnetic field doesn't have an impact on this. So this could be a good evidence of appearance of Kondo effect. In the figure 2, in the graphic, we don't see oscillations, Shubnikov-Dehaz oscillations, comparatively to other whiskers such as indium or gallium stibium. The absence of the oscillations may be attributed to heavy doping of the whisker. Another interesting characteristic of the whisker superconductivity is a small change in the resistance. This fact indicates that existing of superconductive state only in thin subsurface layer of the whisker. The possible mechanism of appearance of superconductivity is a partial superconductivity of the whisker surface. In order to calculate basic superconductivity parameters, we needed to measure upper critical magnetic field. So critical magnetic field is a value of the magnetic field where superconductivity completely suppressed. We carried out a series of measurements for critical magnetic field at different temperature. You can see all of them in figure 3. And using Ginzburg-Landau equation and linear approximation, calculated critical value field is 1.5 Tesla at 0 temperature. Using equation 3, we can calculate superconductor coherent length. Using equation 4, we can calculate superconductive gap of about 0.8 millielectron volts. This value is in a good agreement with literature data. We assume that the most probable mechanism of superconductivity is intercalation of palladium impurity, which was used as initiator of the whisker growth. The intercalation results in appearance of beta palladium bismuth crystals. Coherent length of such crystals is about 20 nanometers. Okay, let's conclude. Temperature dependencies of the resistance of N-type palladium bismuth selenide whiskers with different impurity concentration in the vicinity to the metal insulator transition from the metal side were studied in the temperature range from 1.5 to 77 Kelvin. We observed interesting peculiarities such as sharp drop of the resistance at 0 magnetic field at 5.3 Kelvin. Analyzing the magnetic field influence, we were able to calculate major superconductivity parameters such as upper critical magnetic field, superconductor coherent length, superconductive gap. The strong value of superconductor coherent length, like that it is incorporates, indicates a possibility to observe other exotic phenomena in the whisker bismuth selenide. Also for samples with higher resistivity, so with less impurity, the obvious minimum for resistivity is observed in the temperature range from 20 to 25 Kelvin. That may indicate appearance of a Kondo effect. So that's all. Thank you for your attention.
Thank you very much for your speech, for your topic. Probably we have a question. Do you have a question in Zoom?
I have a question if no one can ask.
Ask a question.
Kyiv National University. You provided expression about the dependence of resistance, and don't remember if magnetic field is present there. The function looks like it has some special function differentiating with one or this one. No, the previous one more, not this one. You have provided for resistance. This is not for resistance.
For resistance.
Yeah, row. You noted this like row. Yeah, like this.
Okay.
Which functions can give you a gap? First of all, and where is the magnetic field there? And it's interesting that your magnetic you have a gap in strong magnetic field for films.
Yeah. So
what this equation describes what? Is it something idealistic model? Does it describe a gap that you discovered in resistance in magnetic field? Thank you.
Okay, thank you for your question. Here, a gap could be assumed, let's say, in the exchange interaction integral. So actually, influence of a magnetic field is presented, let's say, so yeah, it is presented by this exchange interaction integral. So actually, depending on the magnetic field, this integral could have different sign. So sign, yeah, and we can have a different value. That's expression of Kondo effect.
I think I understand. Thank you. So you say J that you introduce it in front of logarithmic dependence changes sign depending on the environment and applied voltage and so on. Thank you.
Thank you very much for the question. Thanks once again to our speaker, and we will move forward.
Thank you.
Our next speaker should be PhD student Mikhailo Barvinko from the Kurdimov Institute of Metal Physics of north of Ukraine. Mikhailo, can you start?
Yes, good day, everyone. Let me just share my presentation. Okay, yes, so hypothetically you have to see it. I think you can see it. So let's begin. Good day, everyone. My name is Mikhailo Barvinko, and I'm the correspondent author. The topic of this presentation is the influence of temperature strain rate on strains of carbene graphene nanoelements. So recently considerable attention is paid to low-dimensional nanoelements, which are a combination of 1- and 2-dimensional nanostructures. Among them, carbene graphene nanoelements, in the future it will be CGN for short, are the most promising from a particular point of view. First of all, they are interesting as elements of strain shronics since they enable changing the width of the band gap when they are deformed. In particular, this makes them indispensable for creating nanolasers with the tunable wavelengths. Effectiveness of the CGN practical use largely depends on the level of their strains and its sensitivity to the temperature. As for our main goals, it would be to establish dependence of temperature on strengths, atomistic mechanisms of temperature influence on carbene-graphene nanoelements fracture, and atomistic mechanism of strain rate influence on carbene-graphene nanoelements fracture. The object in question was two graphene sheets connected by a 10-atom carbene chain. So, a nano device is composed of two infinite half planes of graphene sheet connected by the graphene chain containing 10 atoms. Figure on the top left corner presents the elementary cell of the ordered superstructure which was used to simulate the nano device. Carbene tension gives rise to a change in the width of band gap. It enables to use the chains of carbene as the elements of nanoscale lasers and other optoelectronics, so it would change tunable wavelengths. As formatted and potential molecular dynamics simulation was performed using LAMP software with the included library of interatomic potentials. As a potential for describing the interatomic bond, we were using a fresh developed potential such as machine learning atomic cluster expansion, MLAs for short. That was developed in 2023 by Minyam Gammar, Matus Mrovek, Yuri Lisohorsky, Anton Bochkrev, and Ralph Drotz. An overall assessment of the accuracy of presented ACE parameterization is given in figures that were taken from the original article. Because I'm not the author of this article and it is not our main priority to fully present the MLA's potential, all I can say is that according to the article, the MLA's potential was calibrated for more than 1,000 structures, including carbon, and therefore is more accurate than others' potential. Also, and I quote, the carbon ACE potential opens a new possibility for structural modeling of carbon as atomic scale. It not only describes the fundamental properties of carbon allotropes with theoretical accuracy, but is also able to maintain this accuracy in large-scale simulations. If necessary, the ACE accuracy and transferability can be further improved systematically, either by tailoring on the training dataset for the required application or by extending the ACE basis. End of quote. So as for the MD simulation results, for the first time, it was established from molecular dynamics simulation that there are two different mechanisms of bond breaking in CGN. Comparing to the macro world, we could name them as brittle destruction below 1000 Kelvin and vicious failure above 1000 Kelvin. We're not saying that they're brittle destruction and vicious failure respectively, we are just pointing out that they are similar to them. The so-called brittle destruction characterizes by immediate bond breaking, while above 1000 Kelvin, the bond is shifting alongside graphene sheet independently of a possibility of bond breaking. In this research, we are focusing on the bond breaking below 1000 Kelvin. The fundamental difference between graphene and the CGN is the stochastic nature of the latest. The characteristic of stochastic nature of CGN failure shows in the scattered data of the fracture and growing variance as it shows on the right. The reason of difference between CGN and graphene is the Bayes principle does not apply to CGN because for the carbene chain, the bond breaking is one-time event. Meanwhile, for the graphene, it is necessary to have multiple bond breaking points to destruct the graphene sheet. The coefficient of variance is growing with growing temperature and can be up to 18%, while for graphene it is nearly 0%, which confirms that the stochastic nature of CGN. For fluctuation induced contact bond break under a force field, thermal fluctuation must be picked up by the applied force. This means that the magnitude of critical fluctuation of interatomic distance is predetermined by the level of applied force. In accordance with the fluctuation model proposed by Kotrechko, the first approximation for the probability of contact bond break is the lowest formula. When the contact bond becomes unstable, the potential energy accumulated in the system is released, and this reduces the magnitude of the energy barrier. Breaking bond is a stochastic process, as was mentioned before, and therefore we have to use a statistical model. The statistical model that we want to propose to you contains two main steps: calculating probability of bond breaking for one fluctuation and calculating probability of bond breaking during a specific range of time. Using analytical analysis, it was determined that probability of bond breaking for one fluctuation has exponential form, formula on the left, and the probability of bond breaking can be shown as a probability on the right. According to the proposed theory, the statistical model is working for the temperature range from 0 Kelvin to 1000 Kelvin. However, it is unknown if the theory applies to the temperatures above 1000 Kelvin because our attention was solely focused on the temperatures below 1000 Kelvin. In the future, we want to conduct a research that would be focused on the exploration of the second atomic mechanism of bond breaking above 1000 Kelvin. The magnitude of the contact bond breaking force increases with the strain rate. This is a consequence of the stochastic nature of contact bond breaking and is determined by the reduction in waiting time for critical fluctuations at the current force value. As the deformation rate increases, the rate of force growth also increases. The linear dependence of strains on the logarithm of the velocity is governed by an exponential law for the probability of bond breaking. In conclusion, there are two atomistic mechanisms. The first mechanism is brittle destruction, bond breaking, and the second one is Fischer's failure. The bond is shifting alongside of graphene sheet and then breaking is happening. The fluctuate in dust bond failure is a key reason of temperature-dependent mechanism in CGN. Fundamental characteristic of stochastic nature of CGN failure shows in the scattered data of the fracture. The coefficient of variance is growing with growing temperature and can be up to 18%. And with the growing strain rate, the fracture is growing as well because the waiting time fluctuate induced bond failure is decreasing. Thank you for your attention.
Thank you very much for a nice presentation. Do we have any question? No question yet, so thanks one again, and we will move forward. We will give a floor for a PhD student, Konstantin Korotkov, from
Yes.
Fransevich Institute of Problems of Material Science of NASA of Ukraine. Konstantin, are you ready?
Yes.
Please start. Okay, we can see your
Seen?
Yes.
My talk for determination of magnetization included by DF exchange interaction in ferrum and gadolinium oxide nanostructure. In the present work, we demonstrate a technique for determining the magnetization MDF and the associated effective magnetic field, strange HDF, generated by the exchange DF interaction. This interaction is spin wave interaction with D spin and F spin of electron, established in nanostructures consisting of contacted layers of dimetals, ferrum cobalt nickel, and rare RZM. The ferrum thickness 30 nanometers. It's boundary of Iceland for ferrum and gadolinium oxide in different thickness from 45 to 70 nanometers. Belay film was used as such a nanostructure and composition with a single layer film 30 nanometer films because these films is boundary for Iceland. The nanofilms evaporation in electron beam machine VU 1A. This electron beam machine is modernized with new method. This method can help our the condition this nanofilm because this is not good for
not good in last, and we have modification, and we have these nanostructures. The depositing condition where ferrum is vacuum 3 and in 10 power minus 3 Pascal, nanofilms growth rate 5 to 10 nanometer per minute. Substrate temperature is room temperature, and the gadolinium oxide is this oxide is not stability. This particle pressure is 2 and 10 power minus 2 Pascal. Nanofilm grows rate 3 and 10 nanometer per minute. Prepared by sequentially depositing gadolinium oxide and the firm layer on the substrate. The firm Iceland thickness was 30 nanometers for samples with gadolinium oxide thickness varied between 45 and 30 nanometers. For comparison, a similar thick firm films was deposited on a glass substrate without gadolinium oxide. The end of firm films we coated with copper electrode by thermal evaporation for solidus conductor. These electrodes can help in our structural properties and other properties. The structural properties in this group so we have not structures difference, but this difference in diffractogram is a spin wave voice, and this voice is high to highest magnetic properties. The electronoscopy image of ferrum and layer gadolinium oxide show our this Iceland films, and we have amorphous gadolinium and crystalline ferrum and magnetic. We calculation the tunnel magnetic resistance, and this dependence for different magnetic fields, and we have a saturation in these films, and the differences with these films is effective magnetic films with our interaction. The obtained expression can be used to determine the value, but based of the extremal temporal H dependence. It says dependence saturation. The effective magnetic field is related to magnetic flux by the equivalence. The magnetic is propulsion for effective magnetic fields. And this is dependence of magnetization in 5 polar hyders without effective magnetic fields. And these dependence have a feature linear, and this is line is not different, but scale is different for 10 power 5. Conclusions. A method is proposed to determine the effective magnetic fields, strength, SFD, and the magnetization value caused by the exchange of the interaction. In the ferrum cobalt nickel and rhodium oxide nanostructures in the region of their interface, and exchange of the interaction occurs of a consecutive of GBDJs of wave functions of F and D electrons with unfilled shells. And this function is spin wave voices. This result is an additional magnetization and the corresponding effective field HFD. The method allows the determination of the and that depends on the experimental condition based on the temporal function of effective magnetic field study. It is shown that the rehabilitation propagation region in the ferrum thickness 30 nanometer and gadolinium oxide thickness 17 nanometer. Structure extend to a depth of listed 70 nanometers in the rhodium oxide layers. The value of MFD and HFD obtained for ferrum 30 nanometers and gadolinium oxide 70 nanometers nanostructures are and nanostructures MFD and HFD respectively. Thanks for attention.
Thank you very much for your presentation. Do we have any question? Yes, we have one question in our hall. One moment, please.
Thank you. Maybe even two questions. First one, your values of effective FD field are very small. It's about 10 ampere per meter or 1 microtesla. Do you feel that, do you expect that it is real to detect such small values in any experiment?
The ferrum thickness in 35 nanometers is not Iceland, and this parameter not available. This parameter available for 5 nanometers to 35 nanometers.
Okay.
In 35 nanometers, we have a boundary for calculation, and these Iceland structures don't see.
Okay, and another question, you presented tunnel magnetoresistance ratio in your figure, and one of curve was TMR ratio for pure iron. Maybe I something missed, but how it could be tunneling magnetoresistance in pure iron? What was exactly?
We have pure iron and magnetit, it's ferromagnetics, and this ferromagnetics is intermetallic.
What is the dielectric?
Dielectric, gadolinium oxide and glass.
Okay.
Okay, thank you for your answering. Thank you for the discussion. We will move forward according to our program. Let me see. Do we have a next speaker? The next speaker should be Dr. Vitaly Chorny from the National University of Life and Environmental Science of Ukraine. Vitaly, can you start?
Hello, everyone. Can you see my presentation and can you hear me?
We can see, but on the third slide and not in full screen mode.
Oh, it's not a problem, I hope. Is it okay now?
Not full screen mode. You should stop sharing the screen and then choose the right windows with full screen.
Oh, sorry.
Can you stop sharing and then choose the right windows?
1 moment. Let's try.
Not full screen mode yet. You again choose the window with PPT. You should choose the window with full screen mode presentation.
Still not in full screen?
Now it's not full screen.
Sorry. The first time I can share the screen in full screen mode.
Okay, this is we have some technical issue, but we should move forward because we have a tight program. So please let it do like this.
Let's try this. Good afternoon, everyone. I am Vitaly Chorny from National University of Life and Environmental Sciences of Ukraine. I want to present the study we performed with colleagues from Taras Shevchenko National University and also Institute of Physics of Polish Academy of Science. Our study related with morphology, structure, and optical properties of the glass ceramics based on potassium europium phosphotungstate and on glass of the same composition, of similar composition. What was motivation for our study is the practical application of glass ceramics These materials can be used for light-emitting diodes as covering, and also as covers for solar cells. And it is known that glass ceramics have good physical and chemical properties, much better than glasses and crystalline materials, and also better than silicon and resins that used in light-emitting diodes. And also glass ceramics can be used as sealing materials. And for this reason, they must be they must have low temperature of glassing. So we used such composition for our glasses that allowed to obtain a low crystallization temperature. It allowed to obtain low glass transforming temperature, and also this composition allowed to obtain good optical properties of the glasses and also glass ceramics. We also used good phosphors, red phosphor, potassium europium phosphotungstate. It possesses about 100% quantum yield. That is very high quantum yield for phosphors. And we characterized our glasses and glass ceramics by thermogravimetric analysis, also X-ray diffraction, also optical and scanning electron microscopy, energy dispersive X-ray analysis, infrared absorption, and also photoluminescence spectroscopy. The last one was our main technique. So as seen from this slide, we have very low weight loss in our glasses. So we can state that our glasses have a low degree of hygroscopicity. So they must be stable in humid environment. And also we can see from the right part of the slide that glass transition temperature is about 30 degrees of Celsius, that pretty low, and can be simplified. It simplifies the processing of the glasses and corresponding glass ceramics. Here we can see some optical and electronic scanning microscopy images. At top line, we can see the surface of some glasses of different compositions, and it is seen that samples are very
sorry for interruption. We still see your the first slide.
Oh, I'm sorry. One moment. Try. Can you see my first slide now, or still first?
No, now it's perfect. First slide. Please continue.
Thank you. Thank you. I'm sorry for these issues. And the next, as I said, the top line is some surface of the glasses in optical microscopy. We can see that it pretty smooth, and some crisp and chips can be seen because the glass samples were cutted before optical microscopy studies. Here at part A, we can see small powders, small grains of powders of phosphor. Approximate size of these particles about a few micrometers. But we can obtain from scanning electron microscopy the data that confirms that our phosphor have even smaller about 200 nanometers particles and even less. Also, we can see three pictures, three images of the glass ceramics. It can be seen that glass ceramics and glasses have a similar surface, and in this image we can also see that some crystalline particles are incorporated in the glass host. Detailed study of the glasses by scanning electron microscopy shows that it has very good optical quality and quality in general. And when we move from glass to glass ceramics, we have some inclusions and also waves that correspond to cutted surface of the glass ceramic samples. We studied our samples with X-ray diffraction, and this study has been shown that our powder of the phosphor have good crystallinity, and also in X-ray diffraction patterns of the glasses and glass ceramics, we have almost no narrow lines that shows that our samples mainly are amorphous without enough of crystalline phase. This white bands is typical for glass, especially for phosphate glass samples. Also, we characterized our samples with infrared absorption and transmission spectra. And interesting that transmitting spectra of glass ceramics of two different compositions are almost the same, while the initial glass samples have different infrared transmitting spectra. The main bands in this spectra can be ascribed to phosphate and also to tungstate tetrahedra or octahedra. We studied our samples with photoluminescence spectroscopy, namely photoluminescence excitation and emission spectra. For the initial powder of phosphor, we have luminescence spectra on right plate, and can see that the most intensive bands are located at from 600 to 700 nanometers. That means that our phosphor is red phosphor. This emission, the most effectively excited by direct excitation of europium ions in 380 to 400 nanometers. Here some transitions on this figure, and you can see the most intensive from 7F0 to 5L6. When we added some europium oxide into glasses, we obtained somewhat different pictures than in europium phosphate tungstate phosphor. More wide bands, but in the same positions. Also, if comparing glass ceramics with initial phosphor, we can see similar and some different peculiarities in the spectra. In case of glass ceramics, we have more wider bands of the photoluminescence. That means that europium ions moves toward the glass host. So we have something like partial melt of the phosphor crystallites, and also this europium and also any other elements moves towards the host, glass host. Interesting that under excitation in 350 up to 550 nanometers, there are no luminescence of the glass. But when we move to lower short wavelength excitations, we can see relatively strong emission from phosphotungstate glass. This emission located from 500 up to 800 nanometers. So it covers almost a full visible region and should be taken into account when elaborated optical glass ceramics for light emitting diodes. But in the same time, we still have the most intensive emission band from europium ions in crystalline and also in glass phase. Interestingly, that excitation spectra of the europium in our glass ceramics contain not only direct lines, not only lines of direct excitation of europium ions, but also this luminescence can be excited through absorption of the glass host. So we have energy transfer from glass host to europium ions in glass or in glass ceramics, or in phosphor, I'm sorry. And here are some conclusions. So we used well-known melt quenching technique for elaboration and for synthesis of phosphotungstate glasses and glass ceramics. We obtained the results. Those indicates that our glasses and glass ceramics have low hygroscopicity and are have very good optical properties. Also, our glasses and glass ceramics have low temperatures of synthesis in respect for likely silica or boron-based glasses. We obtained good orange-red luminescence, quite intensive under different excitation of europium ions in this host. And we can conclude that our samples, our materials can be used for elaboration of material for light emitting diodes and solar cell concentrator. So I want to thank organizers and also audience for the attention and also for the financial support. I want to thank Horizon Project and thank you very much.
Thank you for your presentation. And any questions? In Zoom, maybe? We have no questions. Thank you again for your presentation. Next speaker, Professor Yuri Zholodov from Kharkiv National University of Radioelectronics, Ukraine.
Okay, yeah, now it's open. Switched on. Thank you very much for the introduction. It's my great pleasure to be present here. So today I will propose you, let's say, a brief overview of some research results that we have in the field of electrochemiluminescence of thin film modified electrodes, actually, which is conducted at the University of Radio Electronics in the Laboratory of Analytical Optochemitronics. And some part of this research was actually also made in collaboration with our colleagues from Changchun Institute of Applied Chemistry, Chinese Academy of Science. So briefly, for majority of audience, maybe it's not that common topic, so I'll just give a brief introduction of what is ECL, electrochemiluminescence. We are talking about light emission in solutions at the electrode surface during the electrolysis process due to electrochemical generation of some reactive species and appropriate light emission from the near electrode surface. This is like the microphoto of some electrode emitting light. Currently, the ECL has found commercial practical applications mostly in the field of analytics, so it's clinical analysis due to using such approach as ECL immunoassay. But at the same time, there is a lot of interest and a lot of research is ongoing in the field of creating so-called ECL sensors. So ECL on the modified electrodes with different functionality for recognition of different analytes, creating like disposable sensors or durable sensor, depends on the approach, where they have modification of the working electrode of the cell with some recognition elements, some reaction providing elements, and so on, other functionality. To have reaction at the interface between solution and your electrode to give rise of ECL in response of some analytes present in the solution. Just to give you some idea of how these kind of ECL cells or these ECL sensors could look like, here is just some examples, like two ITO electrodes with thin film configuration or ITO GC electrode emerge into some just cell for solution. The electrode modification also is made using different techniques, different nanomaterials, different kind of polymer and organic films, depends on formats. So today I'll just briefly talk about some research we do. Like one of them is using technique called Langmuir-Blodgett, technique for monomolecular organic films deposition from the water-air interface. And when we talk about ECL measurements, we talk about the following. So here is some cell, which means it has some, mostly in most configurations, like 3 electrode cell, reference working and counter electrode connected to the potential state, electrochemical driving device, operating according to some electrochemical program. And the response is recorded in the form of current flow through the working electrode, and mostly the ECL with usually either photodiode, but mostly it's PMT. Photodetector simultaneously recorded as a light and current response with respect to the potential applied to the working electrode with respect to reference. That's the basic of just a regular ECL technique. So with this respect, just a survey, what we started with was the idea that we can use, okay, sorry, mention this slide once again. So here is a representation of the most common widely used ECL reaction in the world, or used for all these analytical systems. There is a stable water-soluble fluorophore dissolved in solution, and some correctant, the most common, some amines like tripropylamine, giving reaction in the solution, so so-called homogeneous ECL reaction. If we are talking about these kind of sensors, in some of the approaches that we are using here, you want to deposit your fluorophore, light-emitting species, into the solution on the surface of your electrode. And this can be done with a variety of techniques, like in particular, as mentioned, the Langmuir-Blodgett technique. But in this case, you will not use the water-soluble fluorophores. You will consider some water-insoluble fluorophores, in particular, those which are well known from early studies of ECL for non-aqueous systems, like in organic solvents, like polycyclic aromatic hydrocarbons. Here should be a Rubran structure, light emit fluorophore with the red emission, orange red emission. And we had such approach, so we tested that it is possible using such non-water soluble fluorophores incorporated in the film of polymethyl methacrylate, maybe also steric acid using Lemur-Blajet technique, and these kind of films are able to give some ECL response when you apply some potential, when you scan your potential from 0 to some maximum point and backwards. There is some light emission occurring at certain point when you reach the reaction potential. This was quite early works. This kind of ECL response is also usually quite proportional to the concentration of your co-reactant, the species with which the reaction takes place in the solution, actually. When we talk about aqueous systems, we always talk about ECL with co-reactant, assuming that you either apply oxidation or reduction potential to your working electrode, and the counter reagent is produced by chemical decomposition of this co-reactant. Like if in this case it is oxidation process on the anode, it means that after oxidation, your co-reactant will generate some reducing species, strong electron donor, okay? And this gives excitation of your fluorophore. That's basically how classical cell systems work currently, those which are used for analytical purposes. Okay, so this was like preliminary studies, and there was a question like, okay, we want to deal with these film-modified electrodes, thin film-modified electrodes. There is many research efforts in the direction of using co-reactants. So tripropylamine is very common, but it is very efficient, known for homogeneous ECL reactions, but it's not very well suitable for ECL on the modified electrode. So it gives emission, but it requires high concentrations. The emission is not very intensive in this kind of results that we got. And at the same time, in our lab, we had other kind of results, preliminary results that we had. We knew that there exists another type of co-reactant, quite different structure, so-called tetraphenylboronic structure, tetraphenylborate of sodium or some other ion, which was known like as a species for synthesis, for analytical chemistry, using some precipitation reactions. And in our lab, it was known that there exists possibility to generate ECL with such species as co-reactant. But this kind of research was abandoned long ago. And then it came time to return back to this system in the aspects of these film-modified electrodes. If we talk about ECL with this co-reactant in aqueous solution with those common fluorophores that I mentioned, like this ruthenium trisbipyridine, water-soluble fluorophore, it is also possible to generate ECL, but not very efficient. So it is working, but it's not very efficient. There are some issues. This co-reactant, that structure shown here, is readily and happily precipitates with other cationic species of organic and inorganic origin. As a result, we will see that we can observe the precipitation of our fluorophore with the co-reactant instead of its participation in ECL reaction. So for those commonly used fluorophores, it happens to be not very suitable. At the same time, it shows that ECL is giving the same spectra as photoluminescence, so a reaction takes place, everything works fine, but there are some issues. There is a saturation of curves with respect to concentration of both fluorophore and TPB at rather low levels. The reason is that you actually have a precipitation when you add co-reactant to the fluorophore, so they create complex which is not water-soluble, so it doesn't work in this form. Additionally, this fluorophore has another bad issue. In water, you have fouling of electrode surface by its oxidation products. So for homogeneous analysis, it's not really very suitable, especially when we talk about aqueous analysis. In aqueous media, that is the main media for any clinical biological research. So seems to be non-suitable. At the same time, this co-reactant was studied also in non-aqueous media, and it showed quite unique properties, which differed very much from those which are currently used in aqueous systems. In particular, using the same Rubran fluorophore in acetonitrile solution, it was showing the possibility to get double ECL peak, which means there are two different processes. Reaction occurs both with oxidized and doubly oxidized cationic and decationic species, which is very unique and was never observed before. And also, But also, it was shown study of the mechanisms of this reaction and a comparison with our results and from results from literature was showing that direct oxidation of this correctant on the electrode, as I mentioned, is producing electrode fouling and also is just consuming your correctant without giving any contribution to the ECL reaction, as opposite to what is happening with the classical correctants, which are often used in the homogeneous medium. Okay, and here we come to the idea of applying this correctant for the field-modified electrodes for creating ECL sensors. So for homogeneous reactions, it's not really suitable, not very practical. And the system on which we were testing this correctant was a similar type of films, but instead of using Lemire-Blanchet technique, we were using spin coating technique as a more efficient, simple for operation. So the glassy carbon electrodes were spin coated with a film of diphenylanthracene, another kind of fluorophore, in the polymer matrix of polyvinylbutyral using ethanol solutions. What is important here? First, for example, diphenylanthracene comparing to previous fluorophores is a blue-violet emission fluorophore. So it means it requires much more energy for this excitation. And for example, the same tripropylamine, commonly used correctant, is not able to provide its ECL emission, not enough energetics of the reaction. So we were producing quite thin films of such polymer fluorophore mixture. Here you can see just an example of such film structure, which has quite porous structure, like microglobular structure. This is atomic force microscopy, and there is a mechanical scratch of your film with the aim of trying to estimate the thickness of this film. It's not more than like 20 nanometers or so. So we are actually using for this spin coating quite diluted solutions, because for thicker films, it doesn't really work. The further experiments of optimization showed that. And when we have this kind of system, so these film-modified electrodes, glassy carbon electrodes with this new correctant type, tetraphenyl braid, when you scan your electrode potential, you get very nice ECL response of quite high intensity with double peaks. So there are two different reaction processes taking place at different potentials. So you can see also the current through the modified electrode, which is just slightly shifted in potential and less in current comparing to the non-modified electrode, meaning your films are like semi-permeable, like microporal structures. The analysis of spectroscopy using optical filters for these two peaks show that they actually have the same shapes, both belong to the diphenylanthracene emission. So no new fluorophores are created, no new states are emitting. So both peaks generate emission from diphenylanthracene. Comparison of influence of film structures shows that, yes, actually there should be a very specific composition of your film in terms of thickness. For thinner and thicker films, the ECL response rapidly decays. Also, there is strong influence of these two peaks ratio and intensity with respect to the doping level of your fluorophore in the polymer. It seems that there is very strong raise of the first peak with the increase of concentration, and the second just gives some moderate. As a result, at proper doping levels, you should be working with the first reaction here, this first peak, giving you much stronger ECL emission. But okay, this we will skip for the moment. But what is the most important is that the fact that we found out that with this specific ECL system, there is also extremely important the so-called scan rate. So previously we were talking about cyclic voltammetry when the electrode potential is scanned from some starting point to some potential and return back. So this is called cyclic voltammetry. So you have like triangular shape excitation signal. And when you increase the scan rate, the intensity of the first peak grows exponentially with the scan rate, while the second just grows slightly and remains unchanged after a certain value. That's because different mechanisms are involved for the first and second peak, and the second peak seems to be absolutely non-useful for our further application. But since we have this kind of dependence, it's evident that we must work with the most with the fastest way of exciting your reaction, which means the pulsed mode ECL. So when you just apply potential pulse to the electrode of certain amplitude, which we found out from the previous studies. And in this case, we are getting very sharply raising very strong ECL response, light emission response, after the potential of oxidation is applied. And due to very high intensity of this ECL reaction, actually, we were forced to start working with very low concentration of our correctant, which essentially solves also the problem of electrode folding and all other issues which we were facing previously in the homogeneous applications with this new correctant. And if you just consider the correctant as the analyte, you can get its ECL response linear dependence on its concentration from the range of some fraction of nanomoles per liter and up to some micromole per liter and maybe further, but it actually happens to be beyond the operation range of our PMT that setup which was used. The only issue with this system, of course, is stability, because this diphenyl-anthracene is not really water-soluble and water-stable fluorophore. It was just the first one to try in terms of this concept of using polycyclic carbons, water non-soluble fluorophores for doping these films. So you can see that if you apply a sequence of pulses, the intensity drops down because it's not really stable in water after oxidation, after the electrochemical oxidation. At the same time, since we are dealing here with very low concentration of correctants, some micromoles per liter and less, it happens that you can consider applying this system for some analytical purposes, because in the process of this reaction, you're generating some reducing agents after the oxidation of your correctant, and this can be intercepted by some oxidants. For example, hypochlorite ion or hydrogen peroxide were tested, and they were readily quenching our ECL emission after increasing their concentration. Also, the problem of stability, there are two ways to address it. One way is, since the electrochemistry is actually the main problem, so it's electrochemical unstable, the fluorophore we are using, we can assume that we could try shorter pulses, and it shows that stability improves from pulse to pulse if you just use shorter potential pulses. But another approach is just considering some other fluorophores. There is a variety of them, which are non-water soluble, to test if they are more stable than this one. This was just the first to try to see if the concept actually working. So let me come to the conclusion then. So what can we say as a conclusion? So we have proposed an approach for incorporating some non-water soluble fluorophores into polymer films on the electrode surface for analytical applications, and using this ECL system with the correctant tetraphenyl borate eliminates all of its problems and exploits all of its benefits. So this correctant is able to excite fluorophores with much higher energetics than commonly used systems. So blue-violet emission of diphenyl-anthracene is not a problem to be excited. With, for example, tripropylamine, you cannot do that. The second thing is that this approach seems to be general, so you can consider a variety of fluorophores, water-soluble fluorophores you can incorporate in such polymer films. And they will also work as this kind of a platform for generating ACL. And then you can already consider analytical applications, either using some additional recognition elements in your film, for example, molecular imprinted polymers, or maybe some immunochemistry components for modification. And the second thing is that the importance of kinetics of this reaction. So pulse mode ECL generates a very efficient, very strong emission, which is not the case, for example, of the same tripropylamine. It's in its mechanism there, and many others of the same sort. They have some reaction steps which are slow and require some time for this chemical transformation to take place after the electrochemical step. As a result, we say that this kind of ECL correctant tetraphenyl borate, and maybe similar structures which also exist, but we never tried it yet, in combination with the film modified electrodes where fluorophores are incorporated into the film on the electrode surface, give a new approach, a new kind of ECL platform, which can be further exploited for analytical applications, and probably we can find variety of such applications. Thank you for your attention. If there are some questions.
Thank you for your presentation. Any questions?
Thank you for your presentation. May you repeat the structure of your films, like polymer and fluorophore? It's 2 layers or it's a
No, it's just a mixture. Polymer fluorophore mixture in a solution, which is spin coated on the surface as a single mixture.
And what is the thickness of such film?
Okay. First of all, it can be seen from this atomic force microscopy. It's like a granular structure. So talking about thickness, it's more like a porous mesh, I would say, a kind of. But if we say like average thickness, maybe depends how to count. Less than 20 nanometers at least. For thicker films, actually, you have reduction of signal. Thinner films, maybe you have not enough substance on the surface, so there is some optimum of dilution. This is actually a polymer concentration with respect to the solvent for this picture that you spin coat.
Maybe did you estimate how such pores or peaks influence on your fluorophore?
Well, not really. Actually, we just estimated how thick is our film, just because spin coating is considered to be a technology for getting thick films. But if you dilute your substance to whatever level you would like, you can get very thin films actually. But the structure is just we use this polymer because like it was convenient and we had it, okay, and it works fine. It doesn't mean this is the best polymer for use for such films or whatever. This was not optimized, but it works very, very nice.
Thank you.
Thank you for the questions and the presentation. The next speaker is Dr. Mikhailo Kurmach from Pisarjevsky Institute of Physical Chemistry of the National Academy of Science of Ukraine.
Good day. Are you hearing me? Okay, let's start my presentation. My presentation is dealing with theorem-containing different catalysts for a process for obtaining different cyclic carbamates and carbonates. Utilization of carbon dioxide is very important task in today's chemistry and ecology and different ecological things. One of the methods for the carbon dioxide utilization is so-called chemical fixation. Using carbon dioxide as a raw material, we can obtain a lot of different materials. For example, different hydrocarbons, methanol, different acids. Among all, cyclic carbonates and cyclic carbonates play an interesting role as materials that have wide industrial importance. For example, cyclic carbonates can be used as precursor for obtaining biodegradable polymers, as chemical as food additives, as electrolytes for lithium ion batteries, and so on. Cyclic carbonates also can be used as precursor for obtaining different chemical substances, for example, different polymers, and so on. A typical method for producing cyclic carbonates and carbamates from amino alcohol, D-alcohol, provides using a so-called phosphan. This material is very hazardous, and changing it by carbon dioxide is a very important task. So it is known that catalysis for these reactions are different materials which will have basic properties. So, for example, typical catalysts for this process are tetra-alkyl ammonium salts that also are hazardous. It's worth noting that some other heterogeneous catalysis is well known as catalysis for this process. For example, titan-containing zeolites, different materials with basic properties. One of them are materials based on cerium oxide. Cerium oxide is well known as catalysis for this process, but now we investigate different types of cerium-containing materials in this work. The aim of our investigation consists in development of cerium-containing catalysis for the production of cyclic carbonates and carbamates. As object, we used cerium O2, mixed cerium magnesium oxides, in which we increase the basicity of our catalyst, and mixed magnesium and cerium materials, so-called nanocomposite of cerium and mixed magnesium cerium oxides on hierarchical zeolites and mesoporous molecular sheaves, such as SB15 and MCM41. Typical method for production magnesium cerium mixed composites consist in so-called method of deposition. On the first stage, precursor of cerium and magnesium oxides were mixed. Then, in case of nanocomposites with added zeolite or mesoporous molecular sheaves, then we precipitated a corresponding oxide using monoethanolamine, and then obtained hydroxides where deposits were calcined at air to obtain corresponding oxide. In case of cerium oxide and cerium containing nanocomposite, we use cerium ammonium nitrate as a rough material. And then we calcinated it at different temperatures to obtain different nanocomposites and different cerium oxides to compare this with nanocomposites. One of the important carriers were obtained, for example, carriers based on hierarchical zeolite were obtained using a so-called Gemini type surfactant. This method provides using so-called special templates, Gemini type surfactants, which have both hydrophilic part in which filtered zeolite is formed, and hydrophobic tails, which are restrict the growth of template and growth of zeolite, and obtaining zeolites with very small size. As we can see, these materials have significantly higher external surface and compared with typical zeolites. As we can see, our final composites based on magnesium oxides on bare zeolites. In this case, we have used cesium-containing zeolites because have the crystallinity of the obtained materials significantly decrease, but these composites possess a very high external surface. Comparing acidic properties of these materials, we can conclude that these materials contain predominantly Lewis acid sites formed by cerium. And also in case of materials, composites which contain a high amount of cerium, bronze stasis sites formed by cerium oxide, we have observed in our samples, both in materials obtained using mesoporous molecular shifts, but also with zeolite beta. Comparing these materials were tested in different methods for obtaining cyclic carbonates. As model molecule, we used styrene and styrene carbonate. This reaction persists in two stages. On the first stage, we used additional oxidant to obtain corresponding epoxide, which on the second stage transformed to corresponding carbonate using CO2. The catalysts for the first stage are typical redox catalysts. They may be titanium oxide, in our case, cerium oxide, while the second stage needs different basic properties. For example, in our cases, we use tetrabutylammonium iodide as co-catalyst, but also as in this reaction works our composite, but significantly lower. As we can see, cerium oxide have lower conversion and lower yield to the target product in comparison with composites, mixed composite magnet-cerium of magnet-cerium oxides. Zeolites obtained these two composites obtained non-aluminum ash form of zeolite beta and mixed magnet-cerium oxide provide significantly higher activity conversion in this process comparing oxide, cerium oxide and magnet-cerium oxide, but selectivity in case of aluminum beta nanoparticle is lower. This is due to the presence of high concentration of branched acid sites, which significantly decreases the selectivity of the process. To increase this selectivity, bronze acid sites in these materials were changed to cesium. Protons were changed to cesium. And these materials have significantly higher activity in comparison with non-exchanged sample. Comparing nanocomposites of magnet-cerium on cesium aluminum beta and MCM41, which have not any, these materials have not in this carrier any bronze acid sites, we can conclude that materials based on cesium aluminum beta is higher. And the conversion of corresponding olefin increases with increase of cerium in our samples. Anyway, selectivity in case of cesium aluminum beta decreases, which we can which we can think that this is due to the presence of bronze acid sites, which decrease our selectivity. In anyway, the presence of cesium allows to obtain a higher yield to the target product in comparison with composites obtained on MCM41. It's worth noting that these composites on magnet-cerium on aluminum and magnet-cerium on aluminum beta nanosheet are active in second stage of the reaction, and their highest yield to the target products were achieved both by to magnet-cerium composite and magnet-cerium mixed oxide and this magnet-cerium composite on aluminum beta nanoparticle. Cerium oxide, we investigated the process of obtaining cyclic carbamate from corresponding amino alcohol. As we can see, based on materials based on cerium are active catalysts for this process. Anyway, the highest activity was achieved for the samples with obtained at calcination temperature 30 and 40, 300 and 400 degrees. Further increase in calcination temperature leads to significantly decrease of activity of catalyst, probably due the presence of low amount of defect. Unfortunately, composites, magnesium on cesium beta nanosheet and CeRO2 on different silicate materials are not active in this process. We can think that this is due to absorption of amino alcohol on weak acid hydroxyl group. Now we're working to increase of activity on these components. Thus, magnesium on cesium aluminum beta nanocomposites are active catalysts for production of cyclic carbonates from under carbon dioxide pressure, both in the catalyst of the second stage and without it. Cerium oxide obtained by decomposition of cerium ammonium nitrate is also an active oxide for the synthesis of cyclic carbonates from carbamates from cyclic amino alcohol. The composition of temperature significantly influences on catalytic properties, and highest yields was achieved at a sample obtained at 300 degrees. Thank you for attention.
Thank you for the presentation. Any questions? In Zoom, maybe? We have no questions. Thank you again.
Thank you very much.
Thank you. And we go to the next speaker. The next speaker will be Professor Olena Rogachova. She will be online. Olena Rogachova from National Technical University, Kharkiv Polytechnical Institute, Ukraine. Olena, are you with us? Are you with us? Olena, we see you are in a waiting room.
Яка Олена?
Рогачова.
А, так, це я.
Your next presentation.
Yes. Скільки?
Yes, now it's in a full screen mode. Please start.
А коли мені починати?
Now, зараз.
Зараз? Так. Good afternoon, everyone. I would like to thank the conference organizers for inviting me to give a talk and present the results of our studies. The topic of my presentation, temperature dependencies of transfer properties of polycrystalline semimetallic bismuth antimony thin films. National Technical University, Kharkov Polytechnic Institute, Department of Physics, Laboratory of Semiconductor Physics and Thermoelectricity. What is motivation? First, currently thermoelectric energy converters are widely used in science and technology, and their areas of application are expanding. Second, solid solutions based on bismuth antimony are known as the best materials for the thermoelectric cooling devices. And the thermoelectric converters based on bismuth antimony in the thin film state are being used more and more widely. And recently, it turned out that bismuth antimony are 3D topological insulators, and interest in the study and transfer properties of bismuth antimony films has grown sharply. In recent years, many works have appeared suggesting the possibility of using of the topological insulators in spintronics, quantum computing, and thermoelectricity. The object of the present study, semi-metallic polycrystalline thin films with thicknesses 28 250 nanometer and with 4.5% of antimony. The bismuth stibium phase diagram is very simple. This solid solution in all region of concentrations. Bismuth stibium crystal structure, yes, the same arsenicum type, but band structure of this system is very complex. You can see that in this system there is region of semi-metal, region of semiconductor, region gate semi-metal. You can see that in this system there are phase transition, semi-metal, semiconductor in best states and other. Earlier, we first observed concentration anomalies of properties and attributed them to a percolation, gapless state, and semi-metal semiconductor transition. And we observe also classical and quantum size effects. Motivation, I continue. It was interesting to find out how similar effects would manifest themselves with changes in temperature, composition, and film thickness. This required a wide range of work related to establishing the influence of composition, thickness of film, and temperature on the transfer properties of thin films. The goal of this work, that is why, to measure temperature, magnetic, and magnetic field dependencies of electrical conductivity, magnetoresistance, Hall coefficient, and charge carrier mobility. Experimental details, very shortly. Transfer coefficient, Hall coefficient, and electrical conductivity were measured in the temperature range 77-300 Kelvin using a conventional DC method. The measurements were carried out on thin film with 6 contacts. To get, it is important, to get the correct concentration electron or Higgs values, Measurements should be carried out in weak magnetic fields, in which the Lorentz force slightly affects carrier movement. Galvanomagnetic effects depend mainly on scattering mechanism. In a weak magnetic field, Hall coefficient remains constant, and the magnetic resistance increases with B according to the quadratic law. That is why, before measuring galvanomagnetic properties, it is necessary to determine the boundary between weak and strong magnetic fields, which was done in this work. However, the authors of most works on the galvanomagnetic properties of this system in thin film states do not indicate the magnitude of the magnetic field at which galvanomagnetic coefficient were measured, which leads to inconsistency in the concentration and mobility of charge carriers values for the same composition. These shapes of samples for measuring electrical conductivity and the Hall coefficient of thin film and bulk crystal and thin. Experimental results, magnetic field dependencies, the boundaries of weak and strong magnetic fields using dependencies of Hall coefficient and magnetic resistance on magnetic field were determined. When N is equal to P, the formula for Hall coefficient and magnetic resistance for semi-metal such. Magnetic field, you can see magnetic field dependencies of Hall coefficient and magnetic resistance for our films with different thicknesses. It follows from the data that up to B induction of magnetic field is equal to 1 Tesla, Hall coefficient does not depend on B, and magnetic resistance varies with the B induction magnetic fields according to a law close to quadratic. That is field can consider weak. This means that measurements of the galvanomagnetic properties bismuth antimony thin films can be carried out in magnetic fields from 0 to 1 Tesla. We used B equal 1 Tesla. Second, sign of the Hall coefficient in these thin films. Unusual situation was observed. Sign of Hall coefficient in films with D less than 90 nanometer was positive, with D more than 90 nanometer negative. But at the same time, at all D, at all thicknesses, negative sign of the Weber coefficient was observed. Unusual situation. Possible explanation. Bismuth crystals has Hall coefficient positive only along trigonal axis, but S coefficient of the Rebecca in any direction remains negative. Bismuth films grown along trigonal axis have positive and the Rebecca coefficient negative. The introduction of stibium leads to a decrease in anisotropy, degree of anisotropy due to appearance of defects, but up to D less than 90 nanometer, some anisotropy is still preserved. But then inversion of Hall coefficient sign occurs. This assumption is consistent with the facts that films with 9% of antimony, we have 4.5% with 9% stibium, and unoriented films have a negative sign of the Hall coefficient regardless of thickness film. This figure, значит, temperature dependencies of the Hall coefficient are films and bismuth films with different D. Third, temperature dependencies of kinetic properties for our films. Electrical conductivity increases with temperature almost linearly. Hysteresis in sigma dependencies on temperature is not observed. Temperature dependencies of sigma during cooling and heating for our films with different D in this. You can see in this figure. Temperature, here the same data are presented in a different way. Instead, electrical conductivity, we use its reciprocal. We use specific resistance rho. And what we observe, the dependence rho on temperature for crystals and thin films are different. For crystals, the thermal resistance coefficient is positive. For films, negative. The rate of decrease in specific resistance with temperature increases as D decreases. For example, for D with thickness 250 nanometer in the range 77,300 Kelvin, electrical conductivity increases by 5 times. For the film with D 48 nanometer, only 2 times. At 77 Kelvin, the value of electrical conductivity for films is significantly lower by 7-12 times than for bulk. But as T increases, temperature increases, the difference decreases and practically disappears at room temperature. Lower values of electrical conductivity in films compared to crystals can be explained by an increase in scattering processes in thin film due to an increase in the contribution of scattering on surfaces and the presence of defects of different types. The fact that at room temperature, the values of electrical conductivity of thin films and crystal practically coincide can be qualitatively explained by the fact that the values of concentration and mobility of charge carrier at room temperature are close both in crystals and in films. The next, magnetic resistance. Temperature dependencies of the magnetic resistance of our films and bismuth films and of different thicknesses. Magnetic resistance observed irregularities. The main parameter that determines the change of magnetic resistance with temperature is charge carrier mobility, and observed irregularities are not difficult to explain by the behavior of the carrier mobility. For example, for 6 films, they is equal to 150 nanometer. Magnetic resistance decreased with increasing temperature, which is consistent with decreasing mobility with increasing temperature. And other regularities also we can explain by this facts. In this figure, I show electrical conductivity, Hall coefficient, and magnetic resistance for the films with different thicknesses together. And in these figures, the temperature dependencies of Hall charge carrier concentration and Hall mobility and separate concentrations and mobilities of electrons and holes for our thin films with shown with thickness 250 nanometer. And in this figure, the same dependencies, only for film with thickness 48 nanometer. In this figure, I show the dependency of electrical conductivity, Hall coefficient, and magnetic resistance for thin films with X is equal 4.5% antimony and 0.09%. We can see that these dependencies very different. Conclusion. For the polycrystalline semi-metallic thin films with 4.5 atomic percent antimony and D is equal 25 250 nanometer, the temperature 77 300 Kelvin, and magnetic field V is equal 0.11 Tesla, dependencies of electrical conductivity, magnetic resistance, Hall coefficient were measured. The boundaries of weak and strong magnetic fields using dependencies of Hall coefficient and magnetic resistance on magnetic field are determined. The influence of thickness of films on the behavior of temperature dependencies and type conductivity in thin films was established. The obtained dependencies were compared with the corresponding dependencies for bulk crystal. The obtained results are important both for development of the concepts of solid-state physics in the field of nanophysics, topological insulators, and thermoelectricity, and for practical applications of this material. Finishing, I would like to say that this is just the beginning of a larger complex of studies of bismuth antimony thin films that we are planning to carry out in the future. We want to study the influence of temperature on quantum size effects and concentration dependence anomalies, which we observed earlier at room temperature. So far, we have established some regularities of the behavior of temperature dependencies of properties only for some thicknesses, but to investigate quantum size effects, we need more the thicknesses. Thank you for your attention.
Thank you for your presentation. Any questions? We have one question.
Olena Ivanivna, just one small question regarding the experimental details. What type of electric contacts did you use for your materials, for your measurements?
What time?
Electric contacts did you use?
Electric contact or contacts or conductivity?
How did you apply electric contacts?
Contacts.
Yes.
No, we use indium contacts.
Thank you.
Usually.
Thank you.
Thank you for your question and your presentation. The next speaker, Dr. Larisa Kunicka from Institute of Macromolecular Chemistry of the National Academy of Science of Ukraine. Larissa, are you with us? Unfortunately, Larissa Kunicka disappeared from our Zoom, and we go into the next speaker, student Antonina Kikot from Lashkaryov Institute of Semiconductor Physics of the National Academy of Science of Ukraine.
Good afternoon, dear audience. I am Antonina Kukut, and I am happy to share with you results of our research, influence of annealing temperature on the electrical properties of nanocomposites, silicon OX, silicon and iron YOZ iron films. This research has been provided based on via Lashkaryov Institute of Semiconductor Physics and Taras Shevchenko National University of Kyiv. Nowadays, iron and silicon nano inclusions in the electric matrices is very perspective material because of their variable properties and possible usage as sensors or as electromagnetic shields. But for their further usage, we need to establish the influence of the annealing temperature on the structural and electrophysical properties of these thin films. So that's why the goal of our research is to investigate influence of the annealing temperature in the range from 400 degrees to 1000 degrees on structural properties of these films. Here you can see the plan of my further report. So let's begin with the film production technology. They were produced by the ion plasma sputtering method, which schematic representation you can see on the picture. Also, films were produced in the argon-oxygen atmosphere using the silicon plus ion target, which you can see on the right picture. To investigate and to understand why we have some peculiarities of these films, we need to investigate their structural properties. So here on the picture, you can see optical microscopy pictures, and we can see the appearing and increasing in diameter nano inclusions. And also we have investigated our films using X-ray spectroscopy. We can see that we have the cubic phase of iron in all samples, and also with the increasing of annealing temperature, we from 600 degrees we can see appearing of magnetite phase, and at the annealing temperature of 1000 degrees we can see crystallization and separation of silicon oxide and magnetite forms. Also, we calculated Gibbs free energy for the possible chemical processes in our films. We can assume that, first of all, because of the amount of Gibbs free energy, magnetite and silicon oxide are formed, but also amorphous phases can be formed. As for the electrical properties, you can see the schematic representation of the current voltage characteristics of our films. We can see very interesting behavior of these characteristics, because we have dielectric type of conductivity, and then it switched to metal type of conductivity. We have transition point, which shifts with increasing of annealing temperature. We have proposed the model to explain this behavior of current voltage characteristics, and we assume that this is because of change of depths of shallow levels, of shallow donor levels. Here on the picture, you can see semi-logarithmic current voltage characteristics for the initial sample, and also conductivity dependence. We can see different areas of behavior of the conductivity dependence on temperature and field. So let's take a look on them. Can you please, the next slide? Oh, thank you. So for the low fields, we we have linear behavior of the current voltage characteristics in the Mott and Afros-Shklovsky coordinates. Also, you can see formulas for the Mott calculations for properties of the film, and here you can see calculated parameters of the film. We assumed that we have a Mott mechanism because we have low critical temperature. For the higher fields, we can describe them by space charge limited conductivity, which is described by the proportion, by the highlighted proportion. But to say that we have this type of conductivity, our M should be higher than 2, and here we calculated M for the different temperatures, and we have these type of conductivity from 90 kelvins to 240 kelvins of measurement temperature. For the higher fields and low temperatures, we have Fowler-Nordheim type of conductivity. We have calculated barrier height, and we see that with the increasing of temperature, barrier height decreases, but with the increasing of field of voltage, our barrier height also increases. For the higher temperatures, we have a Poole-Frankel mechanism, and we have estimated trap depths for this mechanism. After our transition point, where we have switched from the dielectric to metallic type of conductivity, we can see that there is simple Ohm's law. Here you can see the current voltage characteristics for the sample annealed at 1000 degrees, and we also can see that we have different areas with different behavior of conductivity. For the low fields, we also, as for the initial unannealed sample, we may have Mott or Afros-Shklovsky mechanism, and here you can see highlighted by green that we have critical temperature higher than our measurement temperature. That's why there we have Afros-Shklovsky mechanism, and we have calculated parameters for it. For the higher fields, we have it can be described by the SCLC mechanism, and remember that the M should be higher than 2, so we can describe it only up to the measurement temperature 240 kelvins, but for the higher temperatures, we have a Poole-Frankel mechanism. So we have developed a technological process of obtaining these nanocomposite films. Also, the presence of the iron inclusions was determined, and we can see separation of the magnetite and silicon oxide phases with the for the annealed temperature 1000 degrees. Also, the effect of changing the type of conductivity from dielectric to metallic was revealed, and qualitative model was proposed to explain this. As for the mechanism, we established a conduction mechanism. For low fields, we have Mott or Afros-Shklovsky mechanism. For conduction mechanisms for middle fields can be explained using SCLC, and high fields can be described by the Fowler-Nordheim, Poole-Frankel, SCLC, or Ohm's law types of conductivity. Thank you for your attention, and I'm pleased to answer your questions if you have any.
Thank you for your presentation. Any questions?
Please, what was the typical size of inclusions in your materials, and how did it evolve with the annealing temperature? Thank you.
Typical size of inclusions were about 20 nanometers, and the second part of questions I didn't hear
How
clearly.
did it depend on the annealing temperature?
With the increasing of annealing, I can show this on the XRD slide. Here we can see that for ion inclusions, we have at first increasing in the size of our inclusions, but for the 1000 degrees, size of the ion inclusions decreased.
As I understand, you determined the inclusion size from XRD, from the Scherer formula.
Yeah.
Thank you.
Any questions? Thank you for your questions and for your presentation. We return to the previous speaker, Dr. Larisa Kunitska, from macromolecular chemistry of the National Academy of Science of Ukraine.
Can I speak?
Yes.
Yes, yeah. Okay. Hello, everybody. Today we will. I didn't see my presentation. I don't see.
Yes, you can start.
Okay. So today we will talk about hybrid polyion complexes based on polyvinylamine. I should say that this work, this is a result of collaboration between Institute of Macromolecular Chemistry of Kiev and Possibility University of Toulouse. So the object of our presentation, I cannot, okay, next slide, please. The object of our today's presentation are hybrid polyion complexes, HPICs, which appeared when water-soluble block copolymers comprising ionizable complexing block and neutral block interact with polyvalent metal cations in water solution. Such complex formation result in stable nano-object with a core shell structure consisting of a pore rich in complex ions and hydrated shell formed by the neutral blocks. Next, please. HPICs demonstrate high colloidal stability and they attract considerable attention due to their possible application in various fields such as drug delivery, nanoparticles synthesis, colloidal stabilization, growth of inorganic crystals, contrast agents for biomedical applications, and so on. Next, please. There was reported the formation of stable hybrid colloidal suspensions when mixing multivalent metal cations with double hydrophilic block copolymers based on polyethylene oxide and polyacrylic acid, comprising neutral PO block and carboxylate block as an interacting block. But in this work, next please, we use polyvinylamine as an interacting block. It is well known that polyvinylamine is pH-sensitive, water-soluble, non-toxic polymer with a high content of primary amine groups, which easily complex with metal ions. However, HPICs based on polyvinylamine have not been described in literature. We choose two polymer systems consisting of the same polyvinylamine block and different neutral blocks, which are polydimethyl-acrylamide and polyvinylpyrrolidone. We investigated the ability of mentioned block of polymers to form complexes with various metal ions, copper, zinc, cobalt, nickel, and so on. But today's presentation, we will focus on HPICs containing copper ions only. Next, please. To understand the specific features of HPICs formation, we determine the amount of copper ions loaded into the complexes, examine the kinetic of copper loading and copper release, determine the size of HPICs and their stability under different conditions, and reveal the behavior of HPICs in the presence of other ions. Next, please. The process of complex formation between copper ions and amine groups of block copolymers was studied by UV spectroscopy. Increasing amount of copper sulfate was added to the constant amount of PDMA PVA or PVP PVA, so that the molar ratio between copper ions and amine groups of polymer changed from 0 to 1.2. The formation of complex was confirmed by the presence of a band with lambda maximum 592. Above some concentration of copper sulfate, a new band was observed at about 800 nanometers, which means the appearance of free copper ions. Then absorbance was plotted as a function of ratio between copper and amine groups to determine the stoichiometry of the complex formed. A change in the slope was observed at ratio 1:4 for the both block copolymer systems. It should be noted that the same result was previously described in the literature for a complex between polyvinylamine homopolymer and copper ions. Next, please. To obtain the kinetics of copper loading at the molar ratio 1:4 between copper ions and polymer, we followed the evolution of maximum absorbance as function of time directly after addition of copper sulfate to polymer solution. Obtained kinetic graphs show very fast complex formation for both polymer system, which was completed within 5 seconds. Complex formation was also confirmed by conductivity measurements, whereas a copper sulfate solution showed irregular increase in conductivity with increasing of copper concentration. The presence of polymer strongly modifies this behavior. Conductivity was approximately the same, more constant up to this certain point, corresponding to ratio 1:4 or 1:6, and increased after. This is due to the complexation between copper ions and polymer, which prevents the increase of conductivity in the first stage. Once a limit ratio for complexation is reached, the further increase in conductivity is caused by the appearance of free copper ions. This is confirmed by the same slope as observed for pure copper sulfate solution. The Ashpig's formation was also proved by dynamic light scattering. In the absence of copper ions, polymers form polydispersed and large particles in water solution. When copper ions are added, small aggregates appear due to Ashpig's formation. The diameter of these aggregates at ratio 1:4 is about 20 nanometers, both for PDMA PVA and PVP PVA based Ashpigs. Next, please. The protonation of amino groups of polyvinylamine blocks through pH lowering should induce Ashpig's decomplexation and thus copper pH triggered release. In order to verify this statement, a UV spectroscopy experiment were performed. Compositions of copper sulfate with 2 block copolymers at ratio 1:4 were prepared and adjusted at different pH value from 1 to 9. Both systems were found to be stable at pH above 4, and with pH lowering, we observed a decrease in copper binding band caused by decomplexation. Next, please. And at pH 1, next, please. At pH 1, the complete complex destruction occurs very fast and is accompanied by release of free copper ions. Next, please. It was interesting to know whether different ionic strengths affect the Ashpig's object. For this purpose, copper Ashpig samples were prepared in the presence of different amount of 1 molar sodium chloride. As can be seen from UV spectrum, Sodium chloride doesn't lead to destruction of complex, and the ash peaks remain stable even at very large excess of sodium chloride. The small beta-chromic and hyperchromic shift is probably a result of ionic strength changing only. Next, please. Next, please. To check the ability of complexes to exchange with other metal ions, calcium and magnesium ion were added to the copper-loaded ash peaks. UV and DLS measurements were performed for monitoring of copper replacing by these ions. UV spectroscopy didn't show any changes of copper binding band after addition of calcium or magnesium nitrate to ash peak solution. DLS measurement didn't show any changes in the ash peak size after addition of cations too. Thus, we can say that calcium and magnesium ions are not competitors of copper in the process of ash peaks formation. So, we obtained and investigated new hybrid polyion complexes formed by copper ions and polyvinylamine-based block polymers. It was found out that stoichiometry of these complexes is 1 to 4. Complexes are stable at pH above 4 and don't destroy it under the action of sodium chloride. Hydrodynamic diameter of obtained aggregates is about 20 nanometers. And the presence of competing calcium and magnesium ion doesn't influence the ash peak stability. These facts probably can be used to extract copper from the mixture of these ions. Thank you for attention. Some words about application. According to our preliminary experiments, such system could be used as a catalyst and for positron emission tomography, maybe with radioactive copper. So, but these points are under the study. I think we will report our results next time. Thank you for attention.
Thank you. Any question? One question.
Thank you for your presentation. Do you consider the application not only ionic metal, but atomic metals like aurum or argentum?
Aurum or argentum? No, we didn't examine these metals. We worked with I thought about the cobalt, nickel, European, and something. No, aurum and argentum.
Yeah. Thank you.
You're welcome.
Thank you for your question and your presentation. And we go into the next speaker, PhD student Igor Sukhenko from Kurdyumov Institute of Metal Physics of the National Academy of Science of Ukraine.
Greetings, dear colleagues. So, let me start. Next slide, please. Can I? Can you please proceed to the next slide? Or I'm sorry. Okay, thank you. Yeah, let me start. So some of you may have heard the news almost exactly a year ago, when the Korean team reported that they achieved supposedly a room temperature superconductivity in a compound they called LK99, which is a crystal of the apatite type, namely the lead apatite doped with copper. Well, this sparked a huge wave of research in order to try to prove the discovery. And unfortunately, the huge wave of research, as you may see, almost 1,500 articles appeared during this year, overwhelmingly found no evidence of the superconductivity in this compound. But however, it has physical features that initially sparked interest, first of all, among the theorists, and namely that this compound has some analogies to the well-known cuprate high-temperature superconductors. And I'll tell more in the next slides why the theorists initially considered that this compound might have been interesting. So first of all, the main feature of its electronic structure is the flat energy bands at the Fermi level. Their importance in the condensed matter physics is that when the energy bands at the Fermi level tends to be extremely flat, the density of states tends to the infinity, which pushes the system to open some type of a gap in order to optimize its energy. And it may result in different kinds of ordering, namely charge density waves, different types of magnetic ordering, or in fact superconductivity. Well, and it was shown that in this case, the critical temperature may in theory even be enhanced. Well, why from the point of the crystal structure it was interesting? Because the material was of the apatite type, which you may see, and one of the key features of the apatite structures is that they may host a huge variety of so-called isomorphic substitutions. That means that chemically you may replace a lot of components in different atoms in the structure to the other ones, and it provides a useful tool for tuning the properties. Well, in terms of the electronic structure of such compounds, let me first say a couple of words about the role of the crystal symmetry in predicting the properties of the, in determining the electronic structure. Well, the thing is that with the LK99, it was revealed that the preferential type of symmetry, instead of its host compound, which is hexagonal, the symmetry should be broken to the further to the trigonal phase. And despite the differences in energy and in geometry being very small, it leads to significant changes in the electronic structure, which actually leads to the material becoming insulating. And this was one of the main theoretical arguments that proved that LK99 was not, in fact, a superconductor or even a metal. But what is the nature of this type of symmetry breaking? Well, it turns out it was shown also for the cuprate superconductors that sometimes, in case of the strongly correlated electron systems, the strongly correlated effects are actually many-body effects, and that this is why they are difficult to read in terms of density functional theory. But sometimes the DFT calculation may find a broken symmetry solution in which the strong correlated effect treated in a normal correlated regime, but the system is symmetry broken. Even though in nature, in fact, it is symmetry unbroken. So our idea was to, well, why not we try to investigate other compounds that may be similar in structure and some composition to the LK99, but why don't we try to tune their electronic structure in order for at least find some sort of a metallic state? Well, as you may know, the compound being metallic in the normal state, which is a necessary prerequisite for it being superconducting somewhere down the line. Well, so we considered another material. Well, it's lead vanadate apatite doped with copper. And you may see a crystal structure pictured here, depicted here. And the main difference is that those magenta tetrahedra, they are made up of VO4 ions, namely vanadium oxygen ions, instead of phosphorus. Well, you may see the crystal structure parameters obtained from density functional theory calculations. They are in relatively good agreement with the experiment. So let me present you the results of the density functional theory calculations, namely the bond structure and the density of states of this particular compound. Well, it turns out that the picture in terms of when the trigonal symmetry is maintained is actually very similar to that was presented in the numerous LK99 related articles. We also find a pair of flat bands of the copper 3D orbital origin at the Fermi level, with a significant contribution of oxygen orbitals. And here again, we find that triclinic symmetry broken configuration to be more energetically preferred to the symmetry maintained trigonal configuration. However, in this case, what we find is that in contrast to the LK99 case, the metallic state, at least within the DFT framework, is maintained. Namely that no gap is opened at the Fermi level, as you may see on the right side of the slide. Well, this result is puzzling and definitely needs further clarifications. As you know, as some of you may know, the strongly correlated electron systems are very tricky to treat in terms of the DFT. So this result, while promising, is not necessarily a 100% guarantee if it really be in metallic in the normal state. So that may require further investigations with more advanced theoretical methods. And the next step, what we considered, was to consider doping with some, electron doping with selenium. Namely, we replace one of the VO4 tetrahedra with the selenium O4. This is because normally the ionic charge, well, the valency of the CO4 tetrahedron is 6 instead of 5 for the vanadium. And the idea was that if you dope the system with electrons, that should, in principle, stabilize its metallic state. Well, as is the case with a lot of semiconductors, in fact. But instead, we find that, surprisingly, the insulating state is found. Well, the explanation is that, well, this extra charge gets compensated locally, of course, but also the structural distortions that was brought by the introduction of selenium, they outweigh any possible extra charge inclusion effects, namely that the crystal structure gets distorted so much that the effects of the doping become negligible. And let me pass to the conclusions. Well, the idea is that this apatite type crystal structure provides a rich host for constructing materials with new properties, with new unknown before physics, and including the possible search for the superconductivity. Well, what we also found is that the choice of the atom in the apatite tetrahedron strongly influences the geometry of the copper oxygen chemical bonds. And in fact, so strongly that it results in a radical difference when we substitute phosphorus by vanadium, namely the compound becomes metallic in the DFT. Well, also the theoretical tool that we employed was that to try to treat the strong electron correlation with broken symmetry solution. And it worked in case of the LK99, so that's why we decided to employ it here. But also it was discovered that doping by selenium, which was supposed to be electron doping, does not in fact produce a metallic state. It keeps the compound insulating. The results are promising in that sense that it inspires us to further investigations of other compounds down the line, namely to try other types of isomorphic substitution in this lead apatite matrix in order to govern the geometry of chemical bonds and try to bring their parameters closer to currently known families of superconductors, and then who knows what comes of it. In conclusion, I want to acknowledge the support of the National Research Foundation of Ukraine, and of course, thank the armed forces of our country. Thank you for attention, dear colleagues. I will be glad to answer your questions.
Thank you for presentation. Any questions? We have no questions. Thank you again. Dear colleagues, it was the last presentation for today. Thank you for your participation in our second day of conference. We will be waiting for you tomorrow on the third day. Don't forget, today we plan walk excursion across Uzhhorod city at equal 6 o'clock. Thank you.